In the beginning, before there were stars or galaxies, there was only darkness and a single, blazing point of energy. Nearly 14 billion years ago, in a moment beyond comprehension, our universe was born. From an infinitely dense seed, everything burst outward. Space itself expanded, carrying energy and matter with it. This was the cosmic dawn, the Big Bang, the origin of all we know. In that first split second, the universe was unimaginably hot and dense. All the forces of nature were unified as one. As the newborn cosmos grew, it cooled just enough for forces to separate and matter to take shape. What began as a churning sea of energy started forming the first particles, tiny building blocks that would one day become atoms, stars, and galaxies. Time and space unfurled together, the very fabric of reality stretching wider and wider. The early universe expanded at a phenomenal rate. Cosmologists believe that in an instant, the universe underwent a sudden surge of growth called cosmic inflation. In less than a heartbeat, it doubled in size again and again, far faster than the speed of light. This quick burst of expansion took microscopic fluctuations and blew them up to cosmic proportions. Those tiny, uneven spots in the primordial energy became the seeds of everything, the irregularities that gravity would later sculpt into galaxies and clusters of galaxies. As the seconds and minutes passed after the Big Bang, the fireball of creation continued to cool. Particles collided and merged. Protons and neutrons came together, forging the nuclei of the simplest elements. In the first 5 minutes, hydrogen and helium, the lightest and most basic elements, formed in abundance, with a trace of lithium. The young universe was like a hot soup of particles and light. Beyond those first few minutes, it became too cool for further nuclear fusion. The elemental ingredients of the cosmos were set, mostly hydrogen, some helium, and tiny amounts of lithium. Heavier elements did not exist yet. They would be made much later, inside stars that had yet to be born. Still, at this stage, even with atomic nuclei formed, it was far too hot for complete atoms to hold together. Electrons zoomed freely through the chaos, unable to settle into orbit around nuclei. The universe was filled with a brilliant glow, but it was opaque like fog. Light could not travel far without bouncing off free electrons. For hundreds of thousands of years, this dense plasma of charged particles trapped the light, spreading it everywhere, like sunlight caught in thick clouds. As time marched on, the universe kept expanding and cooling. By about 380,000 years after the Big Bang, a remarkable change occurred. The temperature fell enough for electrons to slow down and bind to nuclei, forming the first neutral atoms, mostly hydrogen gas, with some helium. Suddenly, the fog lifted. Space became transparent. Light was free to stream across the cosmos for the first time, unleashing a flood of radiation that had been trapped. This moment is called recombination, when the cosmos went from opaque to clear. The light released at that time still exists today. It has faded and cooled over billions of years, stretching into microwaves as the universe expanded. We see it as a faint afterglow coming from every direction in space, the cosmic microwave background. It is the oldest light we can observe, a gentle whisper from the infant universe. Tiny variations in that background glow appear as faint patches of slightly different temperature. Those patches are the imprints of the first tiny density differences. In them, we can see the seeds of future galaxies. The universe was almost uniform, yet not perfectly so. Gravity, working over immense time, would make the denser patches gather more matter, growing into stars, galaxies, and clusters, while the emptier patches would become the vast cosmic voids. After this release of light, the universe entered a dark age. There were not yet any stars shining. For millions upon millions of years, the expanding cosmos was filled with clouds of hydrogen and helium gas, slowly gathering under the pull of gravity into thicker clumps. The universe was dark and cold, but not inactive. Deep in the densest clumps of gas, gravity was at work, squeezing atoms closer and closer. These clouds grew into proto-galaxies, and within them, more concentrated knots of gas contracted. When the universe was a few 100 million years old, these knots ignited. The first stars were born. At last, points of light pierced the darkness. This was another kind of cosmic dawn, the dawn of starlight. The first stars were likely giants, burning their fuel quickly and brilliantly. They lived short, furious lives, forging heavier elements in their hot cores. When they exhausted their fuel, they died in spectacular explosions, seeding space with the elements of life, carbon, oxygen, and all the rest, that would one day make planets and people. With the birth and death of these early stars, the universe lit up and began to take on the structure we see today. Galaxies formed as swarms of stars bound by gravity, and those galaxies gathered into clusters. The grand cosmic web was emerging, a vast network of matter tracing patterns across the universe. Yet, despite how much we have learned about these early times, the Big Bang still holds deep mysteries. We can describe what happened from fractions of a second onward, but the very first moment, the birth itself, remains elusive. What sparked the Big Bang? What, if anything, came before? We don't have a definitive answer. Time and space as we know them may have begun then, making the question of before almost meaningless. Some theories imagine our Big Bang was just one of many, perhaps an event that sprouted a bubble of space-time in a greater multiverse, or the result of a previous universe collapsing and rebounding. These ideas are speculative, whispering to us that there might be more beyond our cosmic horizon. But for now, they remain in the realm of theory and imagination. We also wonder what powered the inflationary burst that smoothed and expanded the young universe. It solved some puzzles, like why the cosmos looks so uniform everywhere we look. But it raises new questions too. What force caused that explosive expansion, and how did it stop? Was it driven by a strange energy field that vanished after doing its job? The truth is, we are not sure. Inflation is a useful idea, supported by evidence, but the details of how and why it happened are still being puzzled over by scientists peering at faint signals from the dawn of time. Another mystery from the Big Bang era is why the universe has more matter than antimatter. In theory, the Big Bang should have created equal amounts of both, which would have annihilated each other completely, leaving nothing but light. Yet somehow, a tiny fraction of matter survived without being cancelled out by antimatter. That remnant is what formed all the galaxies, stars, planets, and us. Something in those first moments tipped the balance, but we don't yet know exactly what. It's as if the scales of creation were ever so slightly weighted to matter's side, allowing our universe of substance to form. Even with these unanswered questions, the Big Bang theory remains our best explanation for how the universe began and evolved. It is supported by multiple lines of evidence. The expansion of the universe observed in galaxies flying apart, the abundance of light elements like helium, matching predictions from that first nuclear cooking, and the cosmic microwave background glow, mapping out the infant universe. Piece by piece, we have assembled a narrative of our cosmic origins. In our minds, we can try to picture that beginning. All that exists now was once compressed into an infinitesimal point, a singularity of potential. Then, in an instant, space itself blew up like a balloon being rapidly inflated. There was no fireball flying out into empty space. Space was creating itself, carrying matter and light in every direction. The Big Bang was not like an explosion with a center and an edge. It happened everywhere at once because it was the expansion of space itself. And it's still happening today. Our universe continues to grow, galaxies drifting apart like cosmic islands carried on a vast sea. From that primal instant to the formation of the first atoms and stars, the story of cosmic dawn set the stage for everything to come. Every atom in your body, every element on Earth, traces back to that origin. The hydrogen in the water you drink was forged in the Big Bang. The carbon in your cells was formed later in the hearts of ancient stars. But those stars arose because of the conditions the Big Bang created. In a profound sense, we are all children of that moment of creation, carrying pieces of the universe's infancy within us. As we leave the realm of the very early universe and move forward in time, we find that new mysteries await. The Big Bang gave rise to space and matter, but as galaxies began to appear, scientists noticed that something more was needed to explain how those galaxies move and hold together. There seemed to be an invisible presence, a missing ingredient, hiding in the dark. It turned out that galaxies were hiding a secret in plain sight. As astronomers measured stars orbiting in the outer reaches of galaxies, they found something perplexing. The stars at the edges were moving just as fast as those near the center. According to the gravity from the visible stars and gas alone, the outer stars should have been moving more slowly or even drifting away. Instead, they whipped around at high speeds, as if held tight by an extra gravitational force. Clearly, a huge amount of mass was present that we could not see. The same was true in clusters of galaxies. Galaxies orbiting each other moved as though there was far more mass than what shone in telescopes. All this led to the idea of dark matter, matter that gives gravity but emits no light. Dark matter is invisible. It neither glows nor blocks light. It doesn't interact with electricity or magnetism in the usual way. We know it exists only because of its gravity, tugging on stars and galaxies, shaping cosmic structures. It's a bit like noticing the presence of wind by watching leaves dance. We don't see the air, but we see its effects. In the cosmos, we don't see dark matter directly, but we see how it keeps galaxies from flying apart and how it bends the path of light from distant objects. In fact, sometimes we observe the light from a faraway galaxy or quasar curving and distorting, as though passing through an invisible lens. This is called gravitational lensing, and it often reveals massive clumps of dark matter between us and the distant light source, warping space itself. Scientists have deduced that dark matter outweighs the ordinary matter by a significant margin. By current estimates, about 5 times more dark matter exists than normal matter. In other words, the vast majority of matter in the universe is this unseen stuff. All the stars, planets, gas, dust, and living things make up barely a fifth of the total matter out there. The rest resides in this shadow realm, hidden from view. Our own Milky Way galaxy, for example, is enveloped in a giant halo of dark matter. Though we can't see this halo, It extends well beyond the visible edge of the galaxy, and its gravity holds the Milky Way together. Without dark matter's extra pull, galaxies like ours might not have formed in the way they did, or their stars might have drifted apart over billions of years. Dark matter plays a crucial role as the universe's hidden scaffolding. In the early universe, after the Big Bang, there were slight lumps of matter spread about. Because dark matter was so abundant, its gravity started pulling matter, both dark and ordinary, into clumps. Over time, these clumps grew, drawing in gas that formed stars and galaxies. Computer simulations show that if you include dark matter, you naturally get a cosmic web structure, much like what we observe. Filaments of matter stretching across space, with galaxies strung along those filaments like beads on invisible threads. Without the gravity of dark matter, the universe would look very different, and forming galaxies might have been much harder. In this sense, dark matter is an invisible architect of the cosmos, shaping the grand design while remaining hidden in the background. Despite its central role, we still don't know what dark matter actually is. It might be some new kind of elementary particle that simply doesn't interact with light. If so, trillions of these particles could be passing through us every second without a trace. Scientists worldwide have been searching for clues. Huge detectors deep underground are filled with ultra-pure liquids, hoping that once in a great while a dark matter particle will smack into an atomic nucleus and produce a faint signal. So far, these experiments have mostly reported silence, nothing definitive. Physicists at particle accelerators have also looked for signs of dark matter being created in high-energy collisions, but again, no confirmed discoveries yet. Dark matter remains elusive, a shadow that refuses to come into the light. This great unknown spurs many theories. Perhaps dark matter particles are very massive and rare, or conversely very light and abundant. Perhaps they interact only via forces we barely understand. There's even a chance that our theories of gravity might need tweaking to explain some of the observations without invoking dark matter at all. Most evidence, however, strongly supports the idea that dark matter is real and out there. We simply have yet to detect it directly. It is humbling to realize that we understand only a small fraction of the matter in our universe. All our telescopes, all our studies of stars and nebulae, are observing just the tip of a cosmic iceberg, while the bulk of it lurks unseen. For a long time, astronomers thought that this dark matter, along with all the normal matter, would act as a brake on the universe's expansion. After the Big Bang, the universe has been stretching outward, and gravity works against that expansion. It seemed logical that the collective gravity of trillions of stars and vast clouds of dark matter would gradually slow the expansion. The big question was, would there be enough matter to halt expansion entirely and eventually make the universe recollapse in a big crunch? Or would there be too little, letting expansion continue forever, but ever slowing? By the late 20th century, many believed we were close to knowing the answer. They measured the density of matter, visible and dark, and it seemed like the universe was delicately balanced between these possibilities. To test this, astronomers needed to measure the expansion rate over time. They looked at distant exploding stars called Type Ia supernovae, which are useful as mileposts because they shine with almost the same intrinsic brightness wherever they explode. By comparing how bright they appear to us, we can tell how far away they are, and thus how long ago they exploded, since their light took time to reach us. In the late 1990s, 2 independent teams of researchers did this, expecting to see signs that the expansion had slowed down over billions of years. Instead, they found a shock. The distant supernovae were dimmer than expected, meaning they were farther away than anticipated. The universe hadn't slowed its expansion, it had sped it up. The expansion was accelerating, as if some mysterious force were pushing galaxies apart faster and faster. This discovery was so surprising that at first many hesitated to believe it. But more and more evidence quickly supported it. Something was counteracting gravity on the largest scales, causing space to expand ever more quickly. This something was dubbed dark energy. It was a totally unexpected component of our universe, and it appears to make up even more of the cosmos than dark matter does. Suddenly, we realized that roughly 68% of the universe is this dark energy, 27% is dark matter, and only about 5% is the normal matter we once thought was everything. The invisible universe, dark matter and dark energy, isn't a sideshow. It dominates the cosmic balance sheet. We found ourselves in a universe where matter we can see is just a tiny fraction of what's out there. Dark energy raises profound questions. What is this force, or essence, that seems to permeate space? One idea is that it might be a property of space itself, often called the cosmological constant. In this view, even the pure vacuum of empty space has its own energy, and as space expands, more of this energy emerges, fueling further expansion in a self-reinforcing cycle. Another possibility is a new energy field, or fluid that fills space, which we haven't directly detected, but which affects the universe on the largest scales. Physicists give it a simple name, dark energy. But behind that name lies our ignorance. It is a placeholder for a phenomenon we have yet to fully grasp. Interestingly, the notion of a repulsive force in space isn't entirely new. Long before dark energy was discovered, Albert Einstein had introduced a cosmological constant in his equations of general relativity. He intended it as a fudge factor to counteract gravity and keep the universe static, because at the time, the universe was assumed to be unchanging. When evidence of an expanding universe emerged, Einstein reportedly called that constant his greatest blunder and removed it. Yet decades later, the accelerating universe showed that something like Einstein's discarded concept was actually real. The irony is that his supposed mistake may have been an insight ahead of its time, hinting at the very dark energy that now baffles us. The effect of dark energy is subtle on small scales, but monumental over cosmic distances. Within galaxies, or even clusters of galaxies, gravity between stars and other matter is far stronger than the push of dark energy. But across the unimaginable reaches between galaxy clusters, dark energy dominates, inexorably stretching the fabric of space. Over the last few billion years, it has overcome gravity's breaking power on the cosmic scale and taken control of the expansion. As a result, the universe is not only expanding, but doing so at an ever-increasing pace. The space between galaxies grows wider and wider, and over time, distant galaxies appear to speed away faster. What does this runaway expansion mean for the fate of the cosmos? If dark energy remains constant or continues to behave as it does now, the universe will keep accelerating into the far future. Galaxies that are not gravitationally bound to us will recede faster and faster until their light can no longer reach us. Tens of billions of years from now, observers in our galaxy might look out and find an empty void, with all other galaxies slipped beyond the cosmic horizon. The night sky would gradually lose its distant lights, as only the stars of our local group remain visible. Eventually, even those stars will age and die, and no new ones will be born to replace them, leading to a dark, cold universe, expanding into endless night. This is the gloomy projection known as the Big Freeze, or heat death, where the cosmos thins out to near nothingness over an incomprehensible time span. Of course, this assumes dark energy stays consistent. We are not entirely sure it will. Could dark energy weaken or change over time, or even reverse into an attraction? Current observations suggest it acts very much like a constant property of space, but scientists keep checking, mapping the expansion carefully, because any change could signal new physics. Some far-out theories even imagine dark energy could grow stronger in the distant future, leading to a catastrophic scenario dubbed the Big Rip, where every bond is eventually torn apart: galaxies, stars, planets, and even atoms. Fortunately, right now the evidence does not favor that extreme end. It's an exotic idea on the fringe. What we do know is that for the present, dark energy is steering the universe's large-scale evolution, and we are along for the ride. The discovery of dark energy was a humbling reminder that the cosmos can still surprise us. Just when we thought we had a handle on the ingredients of the universe, we found out we were missing most of the recipe. Together, dark matter and dark energy account for about 95% of everything, leaving us largely in the dark about what those substances really are. We gave them simple names, but naming a mystery is not the same as solving it. They remain profound puzzles at the frontier of science, challenges that will occupy curious minds for a long time to come. Even as we grapple with these expansive mysteries of dark matter and dark energy, we turn our attention to another realm of wonder, one much more tangible, yet no less intriguing. While dark energy works on the grandest scale to pull the universe apart, gravity on smaller scales continues to pull matter together. Inside galaxies like our own, stars live out their lives largely unaffected by the accelerating expansion of the universe. And when some of those stars reach the end of their life cycles, they undergo spectacular transformations. In death, certain stars collapse and leave behind exotic remnants, objects so strange they challenge our understanding of physics. Among these stellar ghosts are neutron stars, the incredibly dense cores left after a supernova, which sometimes reveal themselves as pulsating beacons in the darkness. When a massive star reaches the end of its life, it can go out with a spectacular bang, a supernova explosion. In that violent death, the star's outer layers are blasted into space, while the core of the star collapses under gravity. If the original star was big enough, but not too huge, its collapsing core squeezes into an astonishing state: a neutron star. This object is essentially the leftover heart of the star, crushed to incredible density. It's only on the order of 10 or 20 kilometers across, about the size of a city, yet it contains more mass than our sun. Imagine something as heavy as a star compacted into a ball no bigger than Manhattan. The mind reels at such density. Inside a neutron star, atoms as we know them cannot survive. Pressures are so immense that electrons are forced into protons, turning them into neutrons. The entire star becomes one gigantic atomic nucleus, a mass of neutrons packed together shoulder to shoulder. A single teaspoon of neutron star material would weigh billions of tons on Earth, more than a mountain. The gravity at the surface of a neutron star is extraordinarily strong, millions or even billions of times stronger than Earth's gravity. If you could get close, which no one could in practice and live, you'd witness matter in a state beyond anything we experience on Earth, a kind of extreme physics laboratory crafted by nature. Neutron stars are truly cosmic oddities. Though they are born in fiery explosions, once formed, they are extremely dense and stable. They can spin at phenomenal rates. When the core collapsed, it's like a figure skater pulling in their arms during a spin. The star's rotation speeds up dramatically. Some neutron stars rotate dozens of times each second, and some, called millisecond pulsars, have been revved up by feeding on gas from companion stars and can whirl hundreds of times per second. Their spin is so fast that a point on the surface moves at a significant fraction of the speed of light. Despite this frenetic rotation, many neutron stars keep spinning with clockwork regularity. It was the spinning, magnetic nature of neutron stars that led to their discovery. In 1967, astronomers detected an unusual repeating signal, a pulse of radio waves that arrived every 1.3 seconds with uncanny precision. At first, they wondered if it might be a transmission from an intelligent civilization. It was so regular. Half-jokingly, they labeled the source LGM-1 for little green men. But soon, more of these pulsing sources were found, with different rates, ruling out the alien hypothesis. Scientists realized these were spinning neutron stars, sending beams of radio waves into space like lighthouses. These objects were named pulsars, short for pulsating stars. A pulsar works like a cosmic lighthouse. Neutron stars often have extremely strong magnetic fields, trillions of times stronger than Earth's field. Charged particles spiraling around the magnetic poles of the neutron star produce powerful beams of radiation, often radio waves, but sometimes X-rays or gamma rays. The magnetic poles are not aligned with the star's spin axis, so as the star rotates, these beams sweep around through space. If Earth happens to lie in the path of one of those beams, we detect a flash of radiation with each rotation, hence a pulse. To us, it looks like a steady beat, on the order of milliseconds to seconds depending on the pulsar's spin. The effect is like a rotating lighthouse lamp sweeping past our line of sight. Some pulsars spin slowly, maybe once every few seconds, while others spin incredibly fast. The fastest pulsars known spin more than 700 times a second. Imagine an object the size of a city spinning hundreds of times in a single heartbeat without flying apart. It's possible only because of the neutron star's immense gravity and solid structure. These pulsars are stellar clocks, keeping time with astonishing accuracy. In fact, pulsars are so regular that astronomers use them as cosmic timekeepers. By tracking slight irregularities in their timing, researchers can detect gravitational waves gently distorting the fabric of space between us and the pulsar. Neutron stars may be small, but they can have a big impact on their surroundings. Young pulsars often shoot out streams of high-energy particles, creating beautiful, ghostly clouds known as pulsar wind nebulae in the remnants of their parent supernova explosion. Over time, most isolated neutron stars gradually slow their spin and their lighthouse beams dim. The pulses eventually become too faint to detect, and the neutron star becomes quiet, a cold, dark, stellar corpse drifting through the galaxy. Unless it encounters new matter to fuel it, it will simply cool and spin silently for eternity. These stellar ghosts are not always alone. Sometimes they come in pairs. In rare instances, two massive stars in a binary system can both end up as neutron stars orbiting each other. Over eons, they emit gravitational waves and spiral closer together. When they finally merge, the collision is one of the most violent events in the universe. Two city-sized balls of neutrons slam together at a significant fraction of the speed of light, unleashing a burst of energy and forging heavy elements in the process. Such a merger can briefly outshine an entire galaxy and sends ripples through space-time that we can detect as gravitational waves. Not long ago, astronomers observed such an event, the gravitational wave signal from two merging neutron stars, followed by a glow of light from the aftermath that revealed the creation of elements like gold and platinum. It was a spectacular confirmation that even in death, these stars have a creative influence, seeding the cosmos with the ingredients for planets and life. When two neutron stars collide, they often collapse into an even more compact object. In many cases, That final product is a black hole. Neutron stars themselves are in some ways the last step before a black hole. If a dying star's core is more massive than the neutron star limit, around 2 to 3 times the mass of the Sun, no known force can halt the collapse. The core will continue to shrink until it becomes something even stranger. A black hole, a region of space where gravity is so strong that not even light can escape. To explore that ultimate gravitational mystery, we must follow the trail of collapsing stars one step further, into the abyss of a black hole. A black hole is what you get when gravity truly wins. Imagine a star's core, far more massive than the one that formed a neutron star, collapsing without end. The matter keeps contracting tighter and tighter under its own weight, beyond anything we can physically describe, until it creates a region from which nothing can escape. The result is not a solid object in the usual sense, but rather a profound distortion of space and time itself. At the center of this crushed star is what theory calls a singularity, a point of almost infinite density where the normal laws of physics break down. Around that center is an invisible boundary called the event horizon. This is the point of no return. If anything, whether a spaceship, a star, or a ray of light, passes within that boundary, it cannot come back out. To the outside universe, it is as if the object has vanished, swallowed by a literal hole in the fabric of space. Black holes, despite their name, are not exactly holes. They are incredibly dense concentrations of mass, with gravitational fields so strong that escape becomes impossible once you are too close. However, at a distance, the gravity of a black hole is like that of any other object of the same mass. For instance, if our Sun could magically collapse into a black hole of equal mass, it cannot in reality, Earth's orbit would remain virtually unchanged. We would continue to circle an invisible sun-turned black hole as before, though of course all sunlight would be gone and Earth would freeze. The extreme effects of a black hole are felt only when you venture very near to the event horizon. It is there, close to that boundary, that space and time become severely warped. Near a black hole, time itself slows down, relative to an outside observer. If you watched a clock falling toward a black hole, you would see its ticks grow slower and slower as it approached the event horizon, and its light would stretch to redder and dimmer wavelengths. In fact, from our perspective, time for that falling clock nearly stops at the horizon. It seems to hover and fade, never quite seen to cross the threshold. But from the clock's own perspective, or that of an unlucky astronaut falling with it, time would appear to flow normally as they pass the horizon, with no dramatic feeling of crossing any boundary. They would only realize something irrevocable had happened when it was much too late. This strange warping of time and space is a prediction of Einstein's general relativity, confirmed in less extreme conditions, like around Earth or other planets. Near a black hole, these effects become profound. The gravity around a black hole also creates tidal forces of incredible strength. If an object gets very close, the difference in gravity between the side nearer the black hole and the side farther away can stretch it apart violently. In a small black hole, say a few times the Sun's mass, this stretching becomes lethal well before you even reach the event horizon. Any matter or person would be pulled into a long, thin strand in a process whimsically named spaghettification. For a very large black hole, like the supermassive ones in galactic centers, the tidal forces at the horizon might be gentler, and one could actually cross the horizon without immediate spaghettification. Only deeper inside, closer to the singularity, would the ultimate crushing occur. Either way, crossing that boundary means there is no return and no further communication with the outside. It's a one-way journey into darkness, a fall into gravity's abyss, from which no message can be sent back. For a long time, black holes were considered purely theoretical creatures of mathematics. In the early 20th century, when the concept first emerged from Einstein's equations, even Einstein himself doubted that nature could form such objects. It seemed too absurd. A star collapsing to a point, a one-way membrane in space. For decades, many scientists thought something would always intervene to prevent a true black hole. But gradually, evidence began to accumulate. In the 1960s and 70s, astronomers found powerful X-ray sources in our galaxy that hinted at matter heating up tremendously as it fell into an unseen, compact object, likely a black hole feeding on gas from a companion star. One of the first strong candidates was an object called Cygnus X1, an X-ray source with a massive but invisible partner tugging on a visible star. The X-rays from that region suggested that gas was being siphoned off the visible star and swallowed by something dark and dense, releasing high-energy radiation in the process. Meanwhile, the motions of stars at the centers of galaxies provided another clue. Observations showed stars near some galactic cores moving at extreme speeds, as if orbiting an enormous mass that emitted little or no light. In our own Milky Way, over decades, astronomers tracked individual stars in the central region, whipping around an apparently empty spot. These stars reached velocities of thousands of kilometers per second and followed tight, curved paths. By calculating the mass needed to bind those stars in their orbits, scientists discovered a concentration about 4 million times the mass of our Sun, confined in a space no larger than our solar system. Nothing we know of could pack that much mass into such a tiny volume except a black hole. Thus, we are confident that a supermassive black hole sits at the heart of our galaxy, and nearly every large galaxy observed appears to host a supermassive black hole at its core, with masses ranging from millions to billions of suns. Black holes, once speculative, are now an observational reality. Perhaps the most awe-inspiring evidence came in April 2019, when scientists unveiled the first ever direct image of a black hole's immediate vicinity. This was achieved by the Event Horizon Telescope, a global network of radio observatories synchronized to act as one giant telescope. The image revealed the center of galaxy M87 as a ring of glowing, hot gas surrounding a dark, shadowy circle. That dark center was the silhouette of the supermassive black hole itself, casting a shadow on the bright backdrop of the gas swirling around it. For the first time, humanity had seen what a black hole looks like, or at least its shadow. More recently, a similar technique was used to image the radio glow around the Milky Way's own central black hole, giving us another intimate glimpse of these cosmic giants. In addition to imaging them, we have also begun to hear black holes in a sense. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected faint gravitational waves, tiny ripples in space-time, from the merger of two distant black holes. The signal arrived as a very brief chirp in the detectors, representing the final moments of two black holes spiraling into each other and merging to form a larger black hole. Since that first detection, many more such mergers have been observed by LIGO and its partner observatories. These gravitational waves carry information about the colliding black holes, their masses, their spins, and details of their orbiting dance. It is as if, after years of studying how black holes affect their surroundings, we finally caught the universe in the act of two black holes coalescing, and heard the faint ringing of space-time from that cosmic event. The universe has been silently reverberating with such events for eons. Only now do we have the instruments to listen to these cosmic whispers. Despite all we've learned, black holes remain deeply mysterious. The central singularity, if it truly exists as general relativity describes, is a signpost that our understanding of physics is incomplete. To describe what happens at such extreme densities, we will likely need a theory that unites quantum physics with gravity. A quantum theory of gravity that can handle conditions of enormous density and curvature. So far, we don't have that theory fully formulated. However, hints of how quantum physics and black holes intertwine came from the work of physicist Stephen Hawking. Hawking proposed that black holes aren't absolutely black. Instead, they can emit a faint thermal glow, now known as Hawking radiation, due to quantum effects near the event horizon. In essence, particle-antiparticle pairs that constantly pop in and out of existence in empty space can be separated by the black hole's gravity, with one particle falling in and the other escaping as radiation. Over immense timescales, this process can cause a black hole to lose mass and eventually evaporate. For a black hole of stellar mass, this evaporation would take an inconceivably long time, far longer than the current age of the universe. So for all practical purposes, such black holes last essentially forever. Yet the concept that black holes can slowly leak away their mass has deep implications. It led to the famous information paradox. If a black hole eventually disappears, what happens to all the information, the specific details of particles and fields that fell into it? Quantum theory insists that information cannot be destroyed, but a naive view of Hawking radiation suggests it carries no detailed imprint of what went in. This paradox has led to intense theoretical research. Many scientists now suspect that the information is not truly lost, that it might be encoded in subtle correlations within the Hawking radiation, or perhaps stored on the event horizon's surface, in line with a strange idea known as the holographic principle. The true resolution of this paradox is still unknown, making it one of the most fascinating problems at the intersection of gravity, quantum mechanics, and thermodynamics. Speculation about black holes even ventures into the exotic. Some theories propose that the center of a black hole might not be an endpoint at all, but a gateway, or at least connected to another place or time. This brings in the idea of wormholes, hypothetical tunnels through space-time that could potentially connect distant regions of the universe, or even different universes. In fiction, wormholes are portrayed as shortcuts for travel, or portals to other worlds. In theory, Einstein's equations allow solutions that look like wormholes, especially when considering rotating black holes, which might avoid a direct singularity by forming a bridge to a so-called white hole elsewhere. However, there is no evidence that real black holes turn into wormholes, and most physicists believe that any wormhole-like solution would be unstable, pinching off before anything could travel through. Still, the possibility ignites the imagination. Could black holes be more than just destructive gravitational traps? Could they have a creative aspect, spawning new universes beyond our own, or connecting parts of this universe in unexpected ways? These ideas remain speculative, on the fringe of science, but they illustrate how black holes push our thinking to its limits. What we know for certain is that black holes are an integral part of the cosmos and play a key role in the grand scheme of things. They are not just sinks of matter. They can influence their environment dramatically. Supermassive black holes in galaxy centers, when actively consuming gas, can power quasars and active galactic nuclei, some of the brightest objects in the universe. As gas spirals into a black hole's accretion disk, it heats up to millions of degrees and shines brilliantly in X-rays and other wavelengths. Magnetic fields can channel some of this infalling energy into enormous jets that shoot out from the poles of the disk, blasting material for hundreds of thousands of light years. These jets and radiative outputs can affect how stars form in the galaxy, effectively allowing the black hole to regulate the growth of its host galaxy. Thus, paradoxically, the darkest objects in the universe can give rise to some of the brightest phenomena and have a hand in sculpting the evolution of galaxies. From the Big Bang to dark matter and dark energy, from neutron stars to black holes, we have journeyed through an array of deep space mysteries. Black holes, in particular, symbolize a boundary, both a physical boundary in space beyond which we cannot see, and an intellectual boundary beyond which our current theories cannot penetrate. They truly are gravity's abyss, where our understanding falls in and vanishes, leaving us with questions echoing in the void. Yet, as we reach this edge of knowledge, we also feel the excitement of potential discovery. Each mystery we've explored, the origin of the universe, the unseen matter and energy that shape it, the exotic remnants of dead stars, and the fathomless depths of black holes, invites us to push further, to keep asking and observing. We pause here, only briefly, knowing that even stranger and more wondrous cosmic mysteries await us. The universe still has many secrets to whisper. In the quiet of the cosmic night, we will continue our voyage among the stars, ever curious and ever hopeful. The story of discovery continues. Far out in the depths of space, beyond the reach of any telescope, there might lie hidden pathways through the cosmos. These theoretical passageways are known as wormholes, and they capture our imagination with the possibility of cosmic shortcuts. Imagine a tunnel connecting two distant corners of the universe, a mysterious bridge woven from the fabric of space and time. If such a gateway exists, stepping inside might be like walking through a door and instantly emerging light years away beneath an unfamiliar sky. It sounds like fantasy, yet it is rooted in real physics and serious scientific speculation. Wormholes have not only intrigued scientists, but also become a staple of science fiction. Stories and films often portray them as portals for starships or time travelers, whisking adventurers to far-off galaxies in the blink of an eye. These imaginative tales, while fanciful, speak to a deep human longing to overcome the immense distances between stars and find shortcuts where none seem to exist. Through fiction, we explore wormholes as cosmic doorways, reflecting our hope that perhaps the universe has hidden pathways waiting to be discovered. Wormholes were first contemplated by physicists exploring Einstein's theory of relativity. The mathematics suggested that space-time might be able to fold into a tunnel, a bridge connecting two far-flung places. One end of this tunnel could act like a black hole, pulling in anything that comes too close. The other end, according to those same equations, would behave like the opposite, a white hole that only spews things out and refuses entry to anything from outside. In essence, it's as if a black hole could be connected to a strange kind of exit door elsewhere in the universe, forming a cosmic passageway. Such ideas remain purely theoretical. So far, we have never observed a white hole or a wormhole in reality. If they do exist, they might flicker into existence only to collapse almost instantly. In fact, most researchers suspect that any naturally forming wormhole would be unstable, a tunnel that pinches shut before anything can cross through. For an outside observer, a wormhole might resemble a black hole, an intense gravitational well in space. But unlike a true black hole, which simply swallows light, a wormhole could potentially act like a window to a distant realm. If you looked into it, you might see something extraordinary. Perhaps the light from a faraway nebula, or galaxy being funneled through. Scientists have mused that we might detect a wormhole by spotting such odd distortions of light or gravity, but so far, nothing like this has been seen. If wormholes do exist, they are either extremely rare or very well hidden. Even on the tiniest scales, nature might tease us with the idea of wormholes. Some theories propose that at the quantum level, space-time is not smooth, but frothy, full of fleeting little tunnels. These microscopic wormholes would constantly form and evaporate within fractions of a second. They'd be far too small and short-lived for anything, or anyone, to travel through, more like subtle fluctuations in space itself. It's a fascinating thought. At the smallest scales, the universe could be experimenting with these exotic structures, albeit invisibly and impermanently. Some have proposed ideas for keeping a wormhole open. A naturally formed wormhole would snap shut quickly under its own gravity, but if one could thread the tunnel with something that has negative energy or mass, an exotic form of matter not yet known, then in theory it might hold the passage open. This speculation comes from solutions to Einstein's equations that allow traversable wormholes. However, such exotic matter has never been observed, and creating or finding it is beyond our current technology. For now, wormholes and white holes remain inhabitants of mathematical equations and imaginative minds. Yet the allure of these cosmic gateways is hard to resist. One can imagine falling into a wormhole and being swept along on a wild ride through distorted space. Perhaps stars and galaxies would stretch into luminous streaks around you as you hurtle through the tunnel, and gravity itself might shift in strange ways. Then, just as suddenly, you could be gently deposited into a completely different region of the universe, under alien skies filled with unfamiliar stars. It would be a journey beyond any experience we know, a leap across the cosmos unlike any other. As exotic as wormholes are, they raise another astounding possibility: time travel. Space and time are interwoven, so a shortcut through space might also turn into a shortcut through time. If the two ends of a wormhole experience time differently, for instance, if one end travels at near light speed or sits deep in a strong gravitational field, then they will age at different rates. A traveller stepping through such a wormhole could emerge not just somewhere else in space, but also at an earlier or later time. In essence, the wormhole would be acting as a time machine, linking not only distant locations, but different eras. It sounds astonishing, yet it is one theoretical way scientists have imagined moving through time. Travelling into the future, as strange as it sounds, is actually allowed by the laws of physics. In fact, it's something we experience in small measures all the time. If you move very fast, or spend time near a massive object, time will run a bit slower for you, relative to someone who stays behind. Astronauts orbiting Earth, for example, age just a tiny fraction less than they would on the ground, because time for them is passing a touch more slowly. This kind of one-way time travel into the future is a natural consequence of Einstein's relativity. But travelling into the past, reversing the arrow of time, is a very different matter. And here is where we encounter puzzles and paradoxes. Time travel to the past opens a Pandora's box of paradoxes. Changing the order of events can create puzzles that defy logic. If you could journey into the past, you might risk unmaking the present you came from. For instance, imagine you went back in time and somehow prevented your own birth, perhaps by interrupting the chain of events that led to your parents' meeting. If you were never born, how could you have made the trip back at all? This is one of the classic time travel paradoxes, a loop of cause and effect that seems impossible to resolve. Another mind-bending scenario is the bootstrap paradox, a loop where an object or piece of information has no clear origin. Picture a scientist who one day receives detailed blueprints for a revolutionary device from a mysterious visitor. The scientist builds the device according to these plans. Years later, that same inventor travels back in time, carrying the blueprints, and hands them to their younger self, essentially giving them the very plans they will later use. In this case, the design was never created from scratch by anyone. It simply exists in an endless circle, with effect becoming cause. Situations like this challenge our basic understanding of causality, making us wonder what beginning and end really mean in a timeline that loops back on itself. Paradoxes like these suggest there might be deeper rules of nature preventing inconsistencies. Some thinkers have proposed that perhaps the universe has a way of safeguarding itself from true paradoxes. In other words, if you travel to the past, you simply might not be able to change things in a way that creates a contradiction. You might try to alter an event, but something would always happen to preserve the consistency of history, almost as if the timeline protects itself. For example, if you went back to save someone's life, you might inadvertently set in motion the very events that cause their fate, ensuring that history stays consistent. In this view, you going back was always part of the story, and you can't actually rewrite the ending. The universe, so to speak, won't let you kill your own grandfather. Somehow events will conspire to keep the timeline intact. Others imagine a different outcome, that changing the past would create a new, alternate timeline, a parallel world that branches off from the original history. In that case, you could go back and do something differently, and a new reality would sprout where events diverge from that point onward. Your original timeline would remain intact, so you haven't erased your own origin. But now, you'd be in a different branch of history. According to this idea, every change or every choice might spawn a new parallel world. This concept of branching universes hints that perhaps our reality is not the only version of events, but one among countless parallel possibilities. If multiple timelines can exist, why stop at just two? The notion of parallel worlds leads to a profound idea: the multiverse. What if our universe, everything we can see and experience, is just one of countless universes, each with its own version of reality? Some might be very similar to ours, and others drastically different. It's a concept that stretches the imagination to its limit, expanding the stage of existence to a truly cosmic scale. One multiverse theory emerges from quantum physics. It suggests that every time a quantum event or any situation with multiple possible outcomes occurs, all outcomes actually happen, but each in a different universe. In one universe, an outcome goes one way. In another universe, it goes the other way. By this reasoning, the universe would constantly be splitting into many slightly different versions. In one of those universes, perhaps you decided to take a different job, or a certain coin flip landed heads instead of tails, leading history down an alternate path. In another, a big historical event, say a war or an election, might have had the opposite result, creating a world with a different future. The differences can be small or immense, but each possibility becomes real somewhere in the multiverse. In some of those parallel worlds, things might be almost the same as in our reality, with only minor differences, like an old familiar story told with a slight twist. Perhaps in one, the extinction of the dinosaurs never happened because the devastating asteroid missed Earth, and millions of years later, intelligent descendants of dinosaurs evolved instead of humans. In another, Earth might not exist at all. Maybe our solar system never formed, and a different planet around a different star has life and civilizations. With an infinite or near infinite number of universes, Even scenarios that sound like wild fantasy could be realized in some distant branch of reality. Every choice, every chance, every roll of the dice could spin off its own world. Another multiverse idea arises from cosmology. Our universe began with the Big Bang, but some scientists suspect that what we call the universe is just one bubble in a vast cosmic foam. Space itself could be infinite and continuously inflating, with different regions where inflation stops and pockets of universe form, each pocket a bubble with its own Big Bang. Each bubble universe might have its own laws of physics, its own types of particles and forces, maybe even additional dimensions beyond the familiar three of space and one of time. Picture an endless ocean of a higher dimensional space, with bubble universes like floating foam upon it. Our entire observable cosmos would be just one bubble among countless others, isolated from its neighbours by immense expanses of space, or perhaps by dimensions we cannot traverse. These parallel universes, if they exist, are not accessible to us, at least not with any technology we can currently imagine. They lie outside our cosmic horizon, which means no signal or light from them can reach us. The multiverse idea is speculative, but it offers one way to think about some deep mysteries. For example, we often marvel at how our universe's physical laws and constants seem finely tuned for the emergence of stars, planets, and life. In a multiverse, perhaps every possible set of laws exists somewhere among the bubbles or branches. Naturally, we find ourselves in one of the universes that is hospitable, because only in such a universe could observers like us have come about to notice it. In universes with different constants, where no life can evolve, there's no one to wonder at the tuning. This perspective doesn't diminish the specialness of our world, but it suggests that it might not be uniquely designed, just one lucky draw among myriads. Scientists have even searched for subtle evidence that might hint at other universes. One idea was that if another universe had ever collided with ours in the very distant past, during that inflating bubble phase, it might have left a faint imprint. Researchers have scanned the cosmic microwave background radiation, the afterglow of our own Big Bang, for any unusual circular patterns or bruises that could indicate such a collision between cosmic bubbles. So far, they haven't found anything conclusive. It appears that, if other universes are out there, they have left no obvious trace on our own. The multiverse, for now, remains a tantalizing idea on the edge of science, something we can theorize about, but perhaps never directly prove. It expands our sense of what reality could be, even if it forever remains an idea rather than an observable fact. Contemplating the multiverse can make our own existence feel both vast and small. It's humbling to think that our entire universe might be just one of many. Yet, even if reality is so much larger than we thought, we still only experience this one universe of ours. And so, our curiosity returns to the cosmos we know. We wonder about the fate of this universe, our universe. It had a beginning in the Big Bang. Will it have an end? How will the story of our cosmos ultimately unfold? And what will become of the galaxies, stars, and planets in the unimaginably distant future? Our universe had a beginning, and it might have an end. The question of how the cosmos will evolve billions and trillions of years from now has long fascinated scientists and philosophers. For much of the last century, two broad scenarios were envisioned. One possibility was that the universe would expand forever, gradually cooling and fading over infinite time, a fate often called the Big Freeze or heat death. The other possibility was that the expansion might someday reverse if gravity pulled hard enough. A big crunch in which the universe would collapse back into a super-hot, dense state, perhaps even leading to another Big Bang in a cyclic fashion. For a long while, it wasn't clear which destiny awaited us, eternal expansion or eventual collapse. But in the late 1990s, a groundbreaking discovery provided a big clue. Astronomers observing distant exploding stars, supernovae, found that those far-off galaxies weren't just receding, they were receding faster than expected. The expansion of the universe appeared to be accelerating. This was completely unexpected. It implied that some mysterious force, now termed dark energy, is pushing the fabric of space outward, counteracting gravity on large scales. With the discovery of this acceleration, the balance tipped. A big crunch scenario became highly unlikely. Instead, it seems our universe is headed for endless expansion, with dark energy driving galaxies apart faster and faster as time goes on. So, if the universe keeps expanding forever under the influence of dark energy, what does that look like in the very long term? In the relatively near future, meaning billions of years from now, things won't change dramatically overnight. Stars will continue to shine, and galaxies will continue their slow dance. But given enough time, the cumulative effects become significant. In about 4 billion years, for example, our Milky Way galaxy is expected to collide with the Andromeda galaxy, our large neighboring galaxy. This sounds cataclysmic, but such galactic mergers are slow, graceful interweavings that unfold over billions of years. The stars within each galaxy are so far apart that when the galaxies collide, the odds of individual stars crashing into each other are extremely low. Instead, the two vast collections of stars will pass through one another, gravitationally interacting. Over time, their shapes will distort, and they will eventually settle into one larger, merged galaxy, sometimes nicknamed Milkomeda. Future night skies, seen by whatever beings or descendants might exist then, would be filled with new patterns as Andromeda's stars mix with our own. It will be a spectacular sight, perhaps ribbons of stars and clusters strewn across the sky as the two galaxies come together. But after a few more billion years, that excitement will calm down as the new combined galaxy stabilizes. This grand merger is just one early chapter in the far future story. Trillions of years from now, much bigger changes will have unfolded. The expansion of the universe will carry many galaxies so far away that their light can no longer reach us. Our merged galaxy might be essentially alone, with other galaxies too distant to be seen, each isolated in its own expanding bubble of space. Within our galaxy, or whatever galaxies remain bound, the era of star formation will wind down. Stars are born from clouds of gas and dust, but that gas gets used up or locked in remnants over time. Astronomers estimate that in roughly 100 trillion years, 100,000 billion years, the universe will have formed its last new star. All the gas will either be in stars or in dead remnants, or too spread out to coalesce. Eventually, no new stars will form, and the existing stars will age and die. The most massive stars live fast and perish in a few million years. Smaller stars, like our Sun, live for billions. The smallest, dimmest red dwarf stars can burn their fuel slowly for trillions of years. In those far epochs, the only stars still shining will likely be these red dwarfs, glowing faintly red and orange, with perhaps a few white dwarf embers here and there. White dwarfs are the cooling remnants of stars like the Sun. Over an immense span of time, even those will fade. One by one, like candles guttering out, the stars will go dark. Planets, if any still circle the remaining husks of stars, will freeze in the everlasting night, or else wander free through space once their stars are gone. After an unimaginable span of time, even the remnants of stars will undergo further changes. White dwarfs will cool to black dwarfs, cold, dark spheres of carbon and oxygen with no light left to give. Neutron stars and black holes will remain for longer, but they, too, will not last forever. Black holes, those enigmatic gravitational traps, will end up as some of the last massive objects in the universe. For ages, they might slowly swallow any stray matter that drifts too close. But with almost nothing left around, they will mostly just be, slowly losing mass via Hawking radiation. Stephen Hawking predicted that black holes can very gradually evaporate by emitting tiny amounts of radiation due to quantum effects near their event horizons. For a black hole as massive as the Sun, this process is extraordinarily slow. It would take on the order of 10^67 years, that's a 1 with 67 zeros, to evaporate completely. More massive black holes, like the billions of solar mass giants at galaxy centers, would take far, far longer, on the order of 10-100 years or more. But given enough time, even they will evaporate. In that incomprehensibly far future, the last black hole will eventually shrink and vanish in a final quiet burst of energy. What remains after the last black hole evaporates? The universe will be a very different place. No shining stars, no glowing galaxies. All that's left is a thin haze of particles and photons, stretched across an ever-expanding emptiness. The temperature will be just a hair above absolute zero, the coldest temperature possible. This is the twilight of the universe, sometimes called the dark era. With essentially no free energy left to fuel processes, it's a state of deep, eternal quiet. Matter itself might decay over extremely long timescales. If protons are unstable on timescales of, say, 10^34 years, even the atoms might eventually fall apart into radiation and simpler particles. By this final era, all that remains are those elementary particles and very long wavelength radiation, so dilute that on average, you might find only a few particles in volumes as large as the solar system. In such a universe, nothing really happens anymore. It's as close to true nothingness as the universe can get while still existing. Such an ending sounds incredibly bleak and distant. And it is distant, almost to the point of abstraction. Trillions upon trillions of years will pass before the cosmos reaches that final darkness. By comparison, the current age of the universe, about 13.8 billion years, is nothing at all. Every human that ever lived has done so in a youthful, star-filled universe. Our sun still has about 5 billion years of steady burning ahead, and even after it dies, there will be stars shining in the sky for trillions of years. The fact that the universe will perhaps fade one day can feel melancholic, but it's a fate so far beyond any time frame we can truly grasp that it need not trouble us. In the grand timeline of the universe, the era in which beings like us can exist and marvel at the cosmos is like the bright summer of a very long year, with a fall and a deep winter to follow far, far in the future. There are other theoretical fates scientists have pondered, though current evidence makes them seem less likely. One is called the Big Rip. If dark energy isn't constant, but instead grows stronger with time, a scenario sometimes called phantom energy, then it could eventually reach a point where it overpowers all other forces. In the far future, galaxies would be torn apart as dark energy's repulsive push overwhelmed gravity. Then star systems would be ripped open, stars flung away from planets. Closer to the end, even planets and stars themselves might be shredded. And in the final moments, atoms and subatomic particles would be sundered as space itself expands catastrophically. This would be a violent end to the universe, a sort of anti-Big Bang. Fortunately, observations so far suggest that dark energy acts more like a steady property of space, the cosmological constant, rather than something that grows without bound, which means a big rip is not expected. But until we fully understand the nature of dark energy, scientists keep an open mind about such extreme possibilities. Another intriguing idea is that our universe might experience some form of rebirth or transformation instead of a simple heat death. Some speculative models suggest that new universes could bud off from our own. For instance, perhaps occasionally, in the far future, some region of empty space could tunnel into a new state, almost like a phase transition, creating a new Big Bang that expands and forms a new universe, while our old one goes quiet. There's even a concept that our Big Bang might have been spawned by a parent universe, sometimes imagined as the interior of a black hole, leading to a new expansion elsewhere. These ideas are highly theoretical and not strongly supported by evidence, but they're fascinating. They hint that the end might not be the absolute end. In a cyclic model, sometimes called the Big Bounce, a universe could collapse and then explode into a new one, repeating indefinitely. Current data doesn't favor a collapse in our case, but who knows what discoveries lie ahead. Whether one universe or many, perhaps creation and destruction are an ongoing yin and yang. But setting aside those far-out speculations, the simplest expectation given what we see now is that our universe will keep expanding and over an almost eternal timescale fade to black. It's a melancholy vision, but there is a kind of poetic grandeur to it as well. The story of a brilliant cosmos that lives, evolves, and gradually quiets down. And importantly, all of this is in the far, far future. For now, the universe is very much alive with light and energy. Galaxies continue to collide and birth new stars. Stars continue to shine and nurture planets. And on at least one planet, life not only exists, but looks to the skies with curiosity. That brings us back to our present cosmic moment, and one of the most compelling mysteries we can ponder. In this lively universe filled with stars and worlds, is life something rare and precious confined to Earth? Or is it widespread? Are we alone, or are there others? On a small blue planet orbiting an average star, life has thrived for around 4 billion years. Earth is our cradle, and so far the only place we know of that hosts living beings. For most of human history, we could only wonder if other worlds even existed. Now, thanks to modern astronomy, we know that planets are common. The Milky Way galaxy is home to billions of planets, and the universe beyond contains billions of galaxies, each with their own myriad worlds. This explosion of knowledge raises hopes that some of those planets might harbour life, and perhaps even intelligent life. These distant worlds are called exoplanets, and thousands have been discovered over the past few decades. They are amazingly diverse. Some are gas giants bigger than Jupiter that orbit so close to their stars that their atmospheres are blazing hot. Others are small, rocky planets, more akin to Earth, orbiting in zones where temperatures could be mild enough for liquid water. The habitable zone, often described as the region around a star where a planet would be neither too hot nor too cold for liquid water, has been a focal point in the search for Earth-like conditions. And indeed, we've found planets in those favourable zones. For example, astronomers have identified Earth-sized or slightly larger planets at the right distances from sun-like stars and from dimmer red dwarf stars. These discoveries are tantalizing because where there is liquid water, at least on Earth, there is usually life. The more we look, the more it seems that planets are abundant. Virtually every star we examine carefully appears to have at least one planet, and often more. There are likely billions upon billions of planets in our galaxy alone. Even if only a small fraction of them have the right conditions for life, the absolute number of potentially habitable worlds could be in the millions or more. It's a staggering realization. The cosmos may be filled with far more worlds than we ever imagined when we looked up at the stars as points of light. Each one of those stars could be a sun to its own system of planets, some possibly as rich and complex as our own solar system. Life on Earth has proven to be astonishingly resilient and adaptable, which gives us reason to suspect that life, if it starts elsewhere, might also persist in unlikely places. On our planet, we find organisms in extreme environments that would once have been thought utterly inhospitable. There are bacteria and archaea living in scalding water near undersea volcanic vents where sunlight never penetrates. There are microbes in the acidic waters of hot springs and in the bitter cold and dryness of Antarctica's valleys. Life has been found in toxic sludge, inside nuclear reactors, high in the atmosphere, and deep beneath the ground in darkness and pressure. Some microorganisms can survive being frozen for millennia, or being dried out and blasted with radiation. This versatility suggests that if the basic ingredients and energy for life are present, life might find a way, even in conditions very different from the comfortable surface of Earth. Consider Mars, our neighboring planet. Today, Mars is a cold desert with a thin atmosphere where liquid water cannot persist on the surface. But evidence gathered by orbiters, landers, and rovers paints a picture of a very different ancient Mars. Long ago, Mars had flowing rivers, lakes, and maybe a northern ocean. The Curiosity rover, for instance, found rocks that were once mud at the bottom of a lake and detected organic molecules in Martian soil. We've seen dry riverbeds, mineral deposits that form in standing water, and even signs of hot springs or hydrothermal activity in Mars's past. If life ever arose on Mars during those warmer, wetter epochs, perhaps as simple bacteria-like organisms, it might have left traces, fossilized in rocks, or chemical signatures in the soil. Some scientists think there's a slim chance that hardy microbes could still survive today in special niches, maybe in subsurface ice that occasionally melts, or in salty brines that remain liquid at low temperatures. Upcoming missions aim to bring samples of Martian rock back to Earth in the next decade, which could allow us to examine them for microfossils or other biomarkers with the full power of our laboratories. Just finding a single fossilized microbe on Mars, or living one, would be a revelation. It would mean life happened twice in one solar system, implying it could be common across the galaxy. Farther out, the moons of the outer solar system offer some of the best places to search for alien life. Jupiter's moon Europa, for instance, is an icy world a little smaller than our own moon. Beneath Europa's cracked ice crust, there is a deep, global ocean of liquid water. We know this because of Europa's magnetic field and the patterns of its surface cracking, evidence that a conductive, movable layer, like salty water, lies beneath. This ocean might be tens of kilometers thick and contains more liquid water than all of Earth's oceans combined. It's kept liquid by the heat generated from tidal forces. Europa is pulled and squeezed by Jupiter's gravity as it orbits, warming its interior. The result could be an environment somewhat akin to Earth's oceans, especially around hydrothermal vents on the ocean floor. On Earth, such vents, essentially hot, mineral-rich springs on the dark seafloor, are teeming with life, independent of sunlight. Europa likely has similar vents, where its ocean water meets a rocky core, offering chemicals and energy. If anywhere beyond Earth could have independently developed life, Europa's hidden sea is a prime candidate. Saturn's moon Enceladus is another fascinating case. Enceladus is a tiny moon, but it also has a subsurface ocean beneath an icy shell. What's amazing is that Enceladus actively jets water from its ocean into space through geyser-like plumes at its south pole. In 2005, the Cassini spacecraft flew through these plumes and detected water vapor, simple organic molecules, and microscopic grains of rock, hints that hydrothermal processes might be occurring on the seafloor of Enceladus's ocean. In other words, Enceladus has water, heat, and organic chemistry, a trifecta for potential life. Those plume samples didn't show definitive signs of biology, but they confirmed that many building blocks are there. Scientists have even found that the plumes contain tiny particles of silica, which likely come from hot water interacting with rock, much like the environment around Earth's undersea vents. The ingredients for life are present. The question remains whether any biology has taken hold in that dark, subsurface sea. Even Titan, Saturn's largest moon, intrigues astrobiologists, though its potential life would likely be very different from life as we know it. Titan is unique in the solar system. It has a thick atmosphere, denser than Earth's, and is covered in a golden-orange haze. The atmosphere is rich in nitrogen and methane, and at Titan's frigid surface temperatures, 179 degrees or 290 degrees, water is completely frozen as hard as rock. But Titan has lakes and rivers of liquid methane and ethane. It essentially has a methane cycle analogous to Earth's water cycle. Methane clouds, methane rain, filling methane lakes. Titan's landscape features river channels, lakes, and even likely seasonal weather patterns, but with hydrocarbons instead of water. The chemistry on Titan's surface is organic rich. Complex carbon molecules abound. It's conceivable, though certainly not proven, that some form of life could use liquid hydrocarbons as a solvent instead of water. If so, it would be an alien life indeed, with a biochemistry wildly different from ours. Scientists have pondered what signs such life might produce. For instance, unusual deviations in Titan's atmospheric chemistry that might hint at metabolism. So far, Titan's mysteries remain. But even if we don't find life there, it's like a prebiotic laboratory, showing how chemistry might develop in environments very unlike Earth's. Beyond our solar system, we face the challenge of distance. We can't yet send probes to exoplanets. They are far too distant with current technology. But we can use clever techniques to learn about them from afar. One exciting approach is to look for biosignatures in the light from exoplanets. When an exoplanet passes in front of its star, a bit of the starlight filters through the planet's atmosphere, if it has one, on its way to us. By studying that filtered starlight with spectrographs, scientists can determine which gases are present in the planet's air. If one day we detect a combination of gases that on Earth would only coexist due to life, that would be compelling evidence. For instance, oxygen is highly reactive and would normally disappear by forming compounds. But Earth's atmosphere has a lot of oxygen because living plants and algae keep producing it. Similarly, methane in our air comes largely from biological sources and is destroyed by reaction with oxygen over time. Yet Earth has both oxygen and methane because life keeps replenishing them. So, an exoplanet with a similar imbalance, abundant oxygen alongside a gas like methane or nitrous oxide, might be exhibiting a biosignature. As of now, we haven't found such clear signs, but the search has really just begun. The James Webb Space Telescope, launched recently, has the capability to probe some exoplanet atmospheres, especially for larger or hotter planets. In the coming years and decades, improved telescopes on Earth and in space will push toward analyzing smaller, cooler, Earth-like planets. It's conceivable that within our lifetimes, we might detect the faint fingerprints of life on a world dozens of light years away. Perhaps an unexpected ratio of gases, or maybe pigments on the surface, indicating widespread vegetation. Some have proposed looking for a red edge in reflectance spectra that on Earth is caused by chlorophyll in plants. Meanwhile, another strategy in the search for life focuses on listening rather than looking. If intelligent civilizations are out there and use radio or laser signals to communicate, those signals might be detectable over interstellar distances. Since the 1960s, SETI, Search for Extraterrestrial Intelligence, projects have been tuning into the sky with radio telescopes, searching for signals that stand out from natural cosmic noise. They're looking for anything that appears artificial, like a steady, narrow-band radio beacon, or a sequence of pulses encoding information. So far, SETI has not confirmed any alien transmissions. We've heard mostly the static hiss and natural radio emissions of stars, galaxies, and the occasional intriguing blip that turns out to be a pulsar or quasar or interference from Earth's own technology. There have been moments of excitement, like the famous WOW signal detected in 1977, a strong, unexplained burst of radio waves that looked like what an interstellar signal might, coming from the direction of Sagittarius. It lasted a short time, and then was never heard again, leaving us with an enticing mystery, but no proof. SETI continues, now with more advanced equipment, and by scanning more frequencies and more of the sky than ever. The task is enormous, searching through billions of star systems for a signal that might be directed our way, or that we might overhear. It's often likened to trying to detect a faint whisper in a hurricane, or finding a needle in a haystack when you aren't even sure there is a needle. But the payoff, if it happens, would be tremendous. So the listening continues. One challenge with seeking out other civilizations is the vast scale of both space and time. The Milky Way is about 100,000 light-years across, with perhaps 300 billion stars. Our own radio signals, from television, radar, etc., have been leaking into space for only about a century, so they've travelled just 100 light-years outward, reaching only a tiny bubble of stars around us. If an alien civilization lives even 1,000 light-years away, they wouldn't yet know we exist. Our earliest signals won't reach them for 900 more years. Similarly, if they're signalling now but are thousands of light-years from us, it could be millennia before we hear them. There's also the question of timing in a different sense. Civilizations might rise and fall. Humanity has used technology for a blink of an eye compared to cosmic history. It's possible other civilizations came and went millions of years ago, or won't appear until millions of years in the future, so our periods of activity simply don't overlap. The universe is old, 13.8 billion years, and the galaxy could have hosted intelligence long before us, or long after us. We might, by sheer chance, be living in a relatively quiet time or place, cosmically speaking. Still, humanity has made some deliberate attempts to announce our presence, in case someone is listening. Aside from the inadvertent radio and TV leakage, we've beamed a few focused messages out into the stars. One famous instance was in 1974, when astronomers sent a powerful broadcast from the Arecibo radio telescope toward a star cluster called M13, which is about 25,000 light-years away. That message was binary encoded and included crude images representing DNA, a human figure, our solar system, and the telescope itself. It was more a symbolic event than a real attempt at conversation. It will take 25,000 years to get there, and another 25,000 for any reply. We've also put messages aboard spacecraft that are leaving the solar system. The Pioneer 10 and 11 probes carry plaques with a drawing of a man and woman and symbols showing our location and epoch. And as mentioned earlier, the Voyager 1 and 2 probes carry golden records with a wealth of information about Earth. These are like time capsules or bottles cast into the cosmic ocean. The chances of them being found by another civilization are extremely slim, given the vastness of space. But they are there, silently sailing among the stars. As of today, Earth remains the only known oasis of life. This could mean that life is exceedingly rare. Maybe we really are alone, or nearly so. Or it could simply mean that we haven't found the others yet. The question, are we alone in the universe, is one of the deepest and most profound questions we can ask, touching philosophy, science, and even our sense of meaning. It's a question that might not be answered definitively for a long time, but the pursuit of the answer is valuable in itself, driving us to explore and learn more about the cosmos and about ourselves. There is also the notion that intelligent beings might be out there, but deliberately keeping quiet or hidden. Some have whimsically dubbed this the zoo hypothesis. It imagines that advanced civilizations are aware of emerging species like ours, but choose not to interfere or make contact, perhaps to allow natural development, much as zookeepers observe animals without disturbing them. In this scenario, Earth could be observed from afar while we go about our business, not unlike animals in a cosmic safari park. There's no evidence to support this idea. It's more a thought experiment about why, if others are out there, we haven't noticed them. It serves as a reminder that when we ponder the silence of the stars, we have to consider not just physical explanations, like distance or rarity of life, but also possibilities about behavior and choice of potential extraterrestrial intelligences. It's speculation, but it adds another layer to the mystery of our cosmic solitude. On the other hand, imagine for a moment that one day we do receive a clear signal from the stars, unambiguous evidence of an intelligent civilization. Even if the message is simple, "We are here," or too complex to decode right away, the mere knowledge that we are not alone would profoundly change our view of the universe. It would no longer be a question. There would be other minds out there, other stories unfolding on other worlds. We would suddenly have to consider humanity in a cosmic context, one intelligent species among perhaps many. Such a discovery could be an incredibly unifying moment for humanity. Our differences might shrink in importance when we realize that, in the face of a vast universe full of other intelligences, we on Earth are fundamentally one family. Of course, there would be challenges and uncertainties. Who are they? What are their intentions? How do we communicate across maybe dozens or hundreds of light years? But the overarching fact of others out there would stand as a milestone in our history. If instead it turns out that we are essentially alone, or so isolated that, for all practical purposes, we might as well be alone, that realization carries its own weight. It would make us appreciate just how special life is. On a cosmic scale, life might be incredibly precious, a rare gem amid countless barren worlds. An intelligent life capable of culture and reflection might be rarer still. If we are the only technological civilization in our galaxy at this moment, it magnifies the significance of what we do. It would mean the responsibility to cherish and preserve life falls squarely on our shoulders. The extinction of humanity and the other life forms we share Earth with would not just be a local tragedy, but perhaps a cosmic one. The loss of the only known bearers of consciousness. Some thinkers argue that if we are alone, we have a duty to spread life beyond Earth, to seed the cosmos and ensure that the spark of awareness doesn't go out. Others say that whether alone or not, the mere chance that we could be the universe's only self-aware observers should fill us with awe and a profound sense of responsibility toward each other and our planet. Either scenario, teeming universe or lonely universe, is awe-inspiring in its own way. If life is common, the universe is rich with neighbors we have yet to meet, and each new discovery of a living world would be like adding instruments to a grand cosmic orchestra. Imagine the diversity of life forms and perhaps cultures that could be out there. It would be a universe where the drama of life, with all its beauty and struggle, is playing out on countless stages. If we someday contact or encounter another civilization, it could expand our knowledge and perspectives in ways we can hardly foresee, perhaps exchanging art, science, philosophy, bridging an unfathomable gap to find common ground in existence itself. On the flip side, if life is exceedingly rare and we're essentially alone, then we might come to see our own world with even more reverence. Every living thing, from the mightiest whale to the simplest bacterium, would be all the more special, knowing that life is a unique phenomenon in the vast darkness. We would be the universe's sole witnesses to itself, making our thoughts and feelings not trivial, but rather the only narrative the cosmos has, at least in our corner of it. Our quest to find life beyond Earth is, in a sense, also a journey of self-discovery. In searching the skies and analysing distant pinpricks of light, we're forced to define what we're looking for, which makes us reflect on what life is and what makes us who we are. When we listen for a signal, we're acknowledging our own yearning not to be alone. When we scour a planet's atmosphere for signs of biology, we're implicitly asking what conditions made us possible here. The endeavour joins us as one species. All humans share in the wonder of, are we alone? And the hope that we might find cosmic companions, or at least cosmic kin, in the form of simple life. In trying to answer that question, nations and generations have worked together, pointing telescopes skyward, sending probes outward, pooling knowledge. It's a beautiful aspect of science and exploration, this collective longing to know our place in the grand scheme. Across the topics we've explored, cosmic gateways like wormholes, the perplexing paradoxes of time travel, the mind-expanding possibilities of parallel universes, the ultimate fate of everything, and the search for life beyond our world. We've journeyed along the frontier of the known into the vast ocean of the unknown. Each of these subjects stretches our understanding to its limits and invites us to look at reality from a new angle. They remind us that as much as we have learned, we are still at the edge of knowledge, gazing out at a universe full of mysteries. And indeed, each mystery we probe tends to lead to further questions. The more we uncover about the cosmos, the more we appreciate that there is an endless depth to explore. In the quiet of a clear night, under the light of distant stars and galaxies, one can't help but feel a profound sense of wonder. The universe is majestic and humbling, and we are tiny in scale, yet we are a part of this grandeur. The atoms in our bodies were born in stars long dead. The light that falls on our eyes at night might have left its source before we were born. We feel small, but we also feel connected to something enormous and enduring. There's a tranquility in that realization. The same stars we study with curiosity also offer comfort with their steady presence. As you breathe and gaze upward, you are literally inhaling atoms that have cycled through biospheres and perhaps through interstellar space. We are interwoven with the cosmos. We really are made of star stuff. The carbon in our DNA, the calcium in our bones, the iron in our blood. Those elements were forged in the nuclear furnaces of ancient stars and released in supernova explosions that seeded new star systems with the ingredients for planets and life. Our planet, our bodies, everything we see around us is a product of the universe's long history. In a poetic sense, we are a way for the cosmos to know itself. Through our eyes, the universe has seen its own stars, and through our minds, it contemplates its own existence. When we wonder about distant galaxies or the nature of time, it is the universe, in us, wondering about itself. This connection can fill one with a gentle reverence. It means that even if we feel alone, we are never truly isolated. We carry the universe within us, and we are at home in it. Our voyage of discovery is far from over. In truth, it may never end, so long as there are curious minds and open eyes. With every answer we find, new questions emerge. We mapped our solar system, and then we wondered about the stars. We learned about our galaxy, and then about countless other galaxies, and now we speculate about multiple universes. We discovered the building blocks of life, and now we search for life elsewhere. Each step illuminates a little bit more of the path ahead, showing us there's so much more to learn. This constant unfolding of knowledge is one of the greatest adventures we have, and it's an adventure we are all invited to join, simply by wondering, by observing, by asking questions. So, we continue onward, step by step, thought by thought, reaching outward and inward at the same time. The mysteries of the cosmos beckon us, not with loud urgency, but with a soft, persistent call. We follow that call by exploring, by imagining, by striving to understand. It's a journey that unites our species across time. The same stars that guided ancient travelers now serve as subjects for high-tech telescopes. Yet the sense of wonder is the same. We are explorers, even if most of our exploration now is done with instruments and equations and creative ideas. And so, our journey continues. We drift onward in our minds through the vastness, drawn gently by the allure of the unknown. The universe is dark and quiet in many places, but it is not silent to us. Its mysteries speak to our curiosity. We remain calm and unhurried, content to absorb the majesty bit by bit. With each passing generation, we push a little further into the cosmic ocean, keeping our sense of humility and awe. Here on the edge of knowledge, under the endless expanse of stars, we carry the flame of curiosity forward. The night is vast and full of wonder, and we journey through it together, ever calm, ever curious, toward whatever dawn may lie beyond the next horizon. Under a quiet night sky, a giant radio telescope stands in a lonely desert, its dish glinting in the pale starlight. The air is cool and still. Above, countless stars shimmer like distant lanterns. In the silence, this massive ear listens intently, scanning the cosmic darkness for a whisper from the unknown. We have built these instruments to unravel a timeless question. Are we alone in the universe? In our quest to find company in the cosmos, we turn our ears to the sky. Radio waves travel across the vastness of space, and perhaps, somewhere, another civilization is sending them out, deliberately or just as the byproduct of their existence. Our telescopes patiently sweep the heavens, tuning into the static and noise, hoping to catch a faint, meaningful signal. Most nights, it's a quiet vigil. The telescope's receivers register the natural hum of the universe, the hiss of distant stars and galaxies, the whisper of cosmic background radiation. Amid this endless static, we search for something that stands out, a tone or a pattern that nature alone wouldn't produce, a signal that whispers of intelligence beyond our world. We wonder what such a signal might sound like, or what form it could take. It might be a steady beacon, a simple greeting sent across the stars. Or it could be unintentional, the leaked radio chatter of an alien world spilling out into space. Our own planet has been broadcasting for over a century. Early radio and television signals have travelled outwards, forming an expanding bubble now dozens of light years in radius. Any curious listeners in nearby star systems could, in theory, pick up those old echoes of Earth. Likewise, we hope that if other civilizations are out there, they too might inadvertently send their own signals into the dark, signals we could detect. The search for these whispers from other worlds began in earnest in the mid-20th century. In 1960, astronomer Frank Drake aimed a radio telescope at a pair of nearby stars, listening for intelligent transmissions in an experiment charmingly named Project Ozma. It was a modest start, only a few frequencies, a handful of target stars, and it yielded only silence. Over the years, however, the quest grew. More scientists joined the effort, and technology advanced. Radio telescopes became larger and more sensitive. We learned to scan many frequencies at once, to sort through the static with powerful computers. What began as a lone experiment became an international endeavour. SETI, the search for extraterrestrial intelligence. Arrays of dishes now work in concert, surveying the sky for any sign of a crafted signal. It's an immense task, akin to searching for a needle in a cosmic haystack. Every so often, an intriguing signal does emerge from the noise. One famous instance occurred on an August night in 1977. A radio telescope in Ohio detected a strong, narrow-band burst of radio waves coming from the direction of Sagittarius. It lasted just 72 seconds, and then was gone. The signal was so startlingly unusual that the astronomer on duty scribbled, "Wow," next to the data printout, giving this mystery its name, the WOW signal. For a moment, it sparked intense excitement. Could this be a call from another civilization? Researchers tried to find it again, pointing antennas back to that patch of sky many times in the years that followed. But the WOW signal never returned. Whatever it was, perhaps a natural cosmic phenomenon, or a one-time fluke, we were left without answers. To this day, the WOW signal remains an enticing enigma, a glimmer in the data that hints at what we seek, yet refuses to confirm it. The WOW signal remains one of the most tantalizing moments in SETI history, but it stands alone. Over the years, a few other strange radio blips have raised eyebrows, yet none has proven to be the interstellar hello we seek. Often, a promising signal ends up traced back to earthly interference, a distant satellite passing through the telescope's field of view, or a glitch from electronic equipment. At one observatory, researchers once mistook the microwave oven in the staff kitchen for a cosmic signal. The lesson is humbling. The universe is quiet, and when it isn't, we must be sure we're truly hearing another world and not our own echo. So far, nothing has been verified as extraterrestrial. Only silence, punctuated by false alarms, greets our ears. Yet silence has not discouraged us. Instead, it spurs us to broaden the search. We continue to refine our methods and cast a wider net. Not only do we listen in radio frequencies, we also watch the sky for other kinds of signals. Some teams use optical telescopes to hunt for ultra-brief flashes of light, perhaps the burst of a powerful laser directed our way. Such a laser pulse could be a beacon, a cosmic lighthouse flickering for an instant to catch the attention of anyone looking. If an advanced civilization wanted to announce itself, they might choose to send a tight beam of light across space. So we watch and wait for any star that momentarily blinks oddly, any sign of a deliberate flash amidst the darkness. The truth is, we have so much ground to cover. The universe is immense, and our search so far has only skimmed its surface. Consider that there are hundreds of billions of stars in our galaxy alone, and untold frequencies on the electromagnetic spectrum to tune into. Most of our listening has focused on relatively nearby stars, and within certain radio bands. It's been said that if the search space were an ocean, then everything we've done up to now is like taking a single cup of water from that vast sea and examining it. Finding no fish in one cup doesn't tell you much about the rest of the ocean. In the same way, a quiet sky today doesn't guarantee a quiet universe. It may be that we simply haven't searched long enough, deep enough, or in the right way. The silence we encounter now could one day yield to a discovery when we least expect it. While we listen, we have also tried speaking, carefully and in small ways. In 1974, astronomers used the giant Arecibo radio telescope in Puerto Rico to send a brief, powerful broadcast into space. Known as the Arecibo message, it was aimed at a globular star cluster about 25,000 light-years away. The message was essentially a binary-coded note introducing Earth. It included simple images representing our biology and planet, the shapes of a human figure, the DNA double helix, our solar system, and some key numbers. It was a postcard from humanity, meant more as a symbolic gesture than a real conversation starter, since it will take millennia to reach its target. Still, the act of sending it was a bold announcement of our presence. A few years after Arecibo's message, we launched the Voyager probes, robotic explorers that journeyed through the outer solar system and beyond. Affixed to each of them is a golden record, carrying the sounds of Earth and greetings in many languages. On those records are whale songs and laughter, thunder and birdsong, music from different cultures, and a mother's gentle words to her newborn baby. These were the sounds we chose to represent the richness of life on our world. The Voyagers are now drifting in interstellar space, farther from Earth than any human-made object has ever been. In all likelihood, they will wander for millions of years in the cold between the stars. Perhaps no one will ever find them. But if someday someone does, they will discover a tiny time capsule of Earth, a snapshot of our existence in a distant era. Such attempts to reach out are not without debate. Some voices in the scientific community have urged caution. If we announce ourselves to the cosmos, who might hear us? Could there be dangers in making ourselves known to advanced civilizations we do not understand? It is a fair question, born of the same caution one might have shouting in a dark, unknown forest. Others, however, argue that the urge to connect is worth the risk, that the potential benefits of learning from an older, wiser cosmic community outweigh the fears. And perhaps any civilization capable of coming here would be wise enough not to be hostile, or we are simply too small to be of concern. For now, our proactive messages are few and chosen thoughtfully. We send hellos into the dark in the hope that someday we will hear an echo. And so we listen, and we wait. Each passing year of quiet is a gentle reminder of the enormity of the gulf between stars. It may be that light years and eons separate us from our nearest companions, if they exist at all. The silence could mean we truly are alone, or it could simply mean the universe is holding its secrets a bit longer. As we gaze at the night sky, or lean into the static of a radio receiver, we cannot help but wonder, if life is out there, why the hush? Why, amid the billions of stars and planets, do we hear nothing but our own cosmic echo? This haunting question, why the skies are so silent, leads us to one of the greatest puzzles of all, the Fermi paradox. This bewildering silence is at the core of what's known as the Fermi paradox. In simple terms, it asks, if intelligent life is likely in the vast universe, why have we found no trace of it? The paradox gets its name from physicist Enrico Fermi, who reportedly asked in 1950, "Where is everybody?" during a conversation about aliens. It's a question that gains weight with each new discovery of planets around other stars. We now know our galaxy is filled with planets, many of them potentially habitable. By the numbers alone, one might expect a universe teeming with life and even advanced civilizations. And yet, we see no clear evidence of anyone else. The skies, so far, are profoundly quiet and empty of signals or visitors. To grasp the paradox, consider the sheer scale of cosmic opportunity. There are hundreds of billions of stars in the Milky Way and trillions of galaxies beyond. Even if only a tiny fraction of stars have planets with the right conditions, that could still mean millions of life-bearing worlds. And if even a fraction of those produced intelligent life, the galaxy could be home to many civilizations. Some of those might be millions of years older than us. Given enough time, an advanced civilization could conceivably explore or colonize vast swaths of the galaxy. So why don't we see any signs of that? Why isn't our sky lit up with the beacons of alien empires, or our solar system visited by ancient probes? This contradiction between expectation and reality is the essence of the Fermi paradox. One possible resolution is that we are truly alone, or nearly so. Perhaps life, especially complex, intelligent life, is exceedingly rare. The conditions that allowed it to flourish on Earth might be virtually unique. Our planet has benefited from a fortuitous combination of factors: a stable star, a protective magnetic field, an atmosphere, a big moon to steady our seasons, giant outer planets like Jupiter to deflect asteroids, the right chemical ingredients, and billions of years of relatively calm conditions. It could be that very few places in the universe enjoy such a golden recipe. Under this rare Earth perspective, even if microbes exist elsewhere, the leap to an intelligent civilization like ours may happen only once in a blue moon. In that case, we might be the first, or the only, technologically advanced beings in our galaxy, explaining the silence, because there is no one else to speak. Another idea is that simple life might actually be common, while intelligent life is rare. Maybe the universe is filled with microbial oases, bacteria under the ice of moons, algae in alien oceans. But those organisms almost never evolve into spacefaring civilizations. On Earth, it took roughly 4 billion years of evolution for single-celled life to turn into a technological species, us. Complex life required a series of unlikely transitions: the emergence of eukaryotic cells with nuclei, the development of sexual reproduction, the Cambrian explosion of diverse life forms, and eventually, the appearance of creatures with intelligence and dexterity. Perhaps in most places, evolution stalls out before reaching that final step. A planet might forever be home to oceans of microbes or gardens of simple creatures, never producing thinkers that build radios and rockets. If that's true, intelligent civilizations would be extremely scarce, like a few lonely lights flickering in a great darkness. There is also a somber possibility. Perhaps the universe has hosted many advanced civilizations, but they tend to extinguish themselves quickly. In this scenario, life may develop intelligence and technology only to reach a crisis point and falter. A civilization might invent destructive weapons and succumb to war, or overexploit its planet and suffer collapse. It might trigger a catastrophe it cannot survive. Nuclear holocaust, runaway climate disaster, an engineered plague, or an artificial intelligence that escapes control. If most societies destroy themselves or regress before they can spread to the stars, they could blink out of existence without ever meeting one another. The cosmos could be littered with the ashes of extinct civilizations, each one lighting up briefly and then fading long before its signals could reach us. We would hear nothing now, because any who once made noise have already gone quiet forever. Some thinkers propose that intelligent aliens might be out there, but deliberately keeping a low profile. They might observe us without revealing themselves, a concept dubbed the zoo hypothesis. Just as zookeepers try not to startle the animals, advanced beings could be silently watching Earth, allowing us to develop naturally. Perhaps there's a galactic rule against contacting young civilizations until they reach a certain level of maturity. If this is true, the lack of contact is by design. We might be in quarantine, so to speak. In that case, the night sky is quiet, not because we're alone, but because everyone is politely listening and not transmitting, at least not to us. While this idea is speculative, it offers one answer. We haven't heard from others because we're essentially being deliberately ignored or isolated for now. Another angle to the paradox is the possibility that extraterrestrial civilizations are communicating. But we're not picking up the signals because we're looking for the wrong things. Our searches revolve around methods familiar to us, like radio waves or laser flashes. But an alien society, thousands or millions of years ahead, might use communication technologies utterly beyond our current science. They might converse through neutrino beams, quantum entanglement, or dimensions of physics we have yet to discover. Their signals, if passing through our part of space, could be indistinguishable from natural background noise, or simply undetectable with our instruments. It's also possible that advanced beings have moved on from communication altogether as we conceive it, or they communicate so infrequently or subtly that we've missed it. The universe might be humming with alien chatter on channels we haven't learned to tune into. The vast distances and timescales involved present yet another explanation. Even if civilizations are out there and not hiding, they could be so far away that their signals haven't reached us, or ours haven't reached them. The Milky Way is about 100,000 light-years across. If a civilization is on the opposite side, their earliest radio broadcasts would still be tens of thousands of years from reaching us. And we've only been transmitting for a century or so, a blink of an eye. It could be that we're simply too far apart, scattered sparsely across the galaxy. Additionally, civilizations might not last long, as mentioned, so two civilizations might rarely overlap in existence at the same time. They could rise and fall millions of years apart. We might have just missed another society that flourished eons before us. and another might arise long after we are gone. In the cosmic timeline, neighbors could easily miss each other. Could it be that aliens have, in fact, been here, and we just don't have evidence? Some people have speculated that extraterrestrials visited Earth in ancient times, perhaps inspiring myths or marvels. Others wonder if UFO sightings in modern times are evidence of alien observers. However, despite the folklore and occasional sensational claims, rigorous scrutiny has yet to yield concrete proof of alien visitation. No confirmed alien artifacts have been found, and phenomena like UFOs remain unexplained but not proven to be extraterrestrial. If advanced aliens wanted to study us without interference, they likely could do so undetected. So while we can't entirely rule out that someone has passed through our cosmic neighborhood, there's nothing definitive to support it. The paradox remains. By all appearances, we have no company. It's also conceivable that humanity is simply one of the first intelligent civilizations to emerge. The universe is 13.8 billion years old, but perhaps the conditions for life have only recently become favorable in our galaxy. Heavy elements needed for planets and biology took time to accumulate in the cosmos. There's a notion that life might arise more frequently around stars that formed later, after previous generations of stars seeded the galaxy with rich chemistry. If Earth happened to be ahead of the curve, we could be among the pioneers of intelligence. In that case, other civilizations might come into being in the future, long after we're gone, or we might eventually become the ancients that newer species look for. Being first is as good an explanation for the silence as being alone. If no one else has had time to get going yet, then the night sky would indeed be quiet. All these hypotheses, and more, have been proposed to resolve Fermi's haunting question. Perhaps the truth involves several factors together. At this point, we simply don't know. The Fermi paradox remains an open-ended riddle, reflecting both our hopes and our fears about our place in the cosmos. It forces us to confront possibilities that are by turns reassuring, maybe we are special, and disconcerting, maybe intelligent life tends to self-destruct, or maybe an unseen galactic club is shunning us. The paradox persists because we lack data. We have just one example of life, us, and one known inhabited planet, Earth. Until we find evidence of another, whether it be a microbe under a Martian rock or a message from a distant star, we are left to wonder and theorize. The silence of the universe is a canvas on which we paint our ideas. It challenges us to keep searching, to either discover that we are not alone, or to understand why, against all odds, we might be. One concept that arises often in these discussions is the idea of a great filter. The great filter is essentially a way to explain the Fermi paradox by positing a nearly insurmountable barrier on the path to interstellar civilization. In other words, maybe there's a step in the evolution of life that is so hard almost no one gets past it. This concept has profound implications for us. If the filter is behind us, we might be an exceedingly rare success story. If it lies ahead, we could be heading toward a fate that has stopped countless civilizations before us. Let's delve deeper into what this great filter might be, and what it means for our search for company in the universe. The great filter hypothesis suggests that at least one critical stage in the long journey from stardust to a spacefaring civilization is extremely unlikely. To illustrate, think of all the steps required for us to be here now. Contemplating the cosmos, a star with planets, life arising from chemistry, simple single cells evolving, complex cells emerging, multicellular life diversifying, intelligent animals developing, a tool-using civilization, and then the leap to colonizing beyond one's home planet. The great filter could be any one of those steps, whichever one is vanishingly rare or difficult. If the filter is an event in the distant past, it would mean we've passed it. If it's in our future, it means a daunting challenge still awaits that most fail to overcome. If the great filter lies in our past, some step that happened on Earth was an extraordinary fluke. It could be the emergence of life itself, maybe the formation of self-replicating molecules, the first DNA or RNA, is practically a miracle. Or perhaps once life began, getting from simple single-celled bacteria to the more complex eukaryotic cells was the real hurdle. On Earth, it took over 2 billion years to happen. Some even point to the jump to multicellular life, or the evolution of intelligence, as the tough step. If any of these are incredibly improbable, it would explain why the universe seems devoid of peers. Nearly all planets never get that far. We might be among the lucky few on which, by chance, the dice rolled favorably. In that case, the cosmic silence is actually good news for us. It implies we've already done what almost no one else could. On the other hand, if the great filter is ahead of us, it is a worrisome prospect. That would mean one of the steps we have yet to take, or are in the middle of right now, almost always leads to failure. Often people speculate that this future filter could be a self-inflicted catastrophe that advanced civilizations trigger. For instance, the invention of powerful technologies might almost inevitably lead to disaster. Nuclear war, runaway artificial intelligence, bioengineered pandemics, or ecological collapse. It might also be something external. Perhaps environments on inhabited planets tend to destabilize, or cosmic events, like supernovae or asteroid bombardments, frequently wipe civilizations out at a certain point. If the great filter awaits us, the silence out there could be an ominous warning. The universe may be whispering that many have come this way before, only to reach a point of no return. It would urge us to be exceptionally careful in the coming centuries. The great filter concept leads to an unsettling kind of detective work. We can look for clues about whether the filter is behind or ahead by searching for life elsewhere. Consider this. If we discover even simple life relatively nearby, say fossils of microbes on Mars, or microorganisms in the ocean of Jupiter's moon Europa, it would tell us that life can start in more than one place. That would imply the beginning of life might not be the filter. It happened twice in one solar system. Paradoxically, that would be bad news, because it suggests the filter likely comes later. Perhaps the hard part is the emergence of complex life, intelligence, or surviving technological adolescence, which might still be in front of us. Conversely, if we scour Mars, Europa, and beyond and find nothing, it might mean that abiogenesis, life's start, is extremely rare. If Earth was the only place life got going, then the filter was at the very beginning, and we passed it. That scenario would make our existence incredibly special, and perhaps give us better odds that nothing inevitable will snuff us out anytime soon. The notion of the great filter makes our present era feel especially significant. If the filter is ahead, humanity may be approaching a crucial test that many others did not pass. This perspective can be seen as a call for caution and wisdom, to manage our technologies and planet carefully, to avoid the pitfalls that could end our story. We might strive to become the exception, the civilization that navigates through the dangerous window and continues to thrive. On the other hand, if the filter is behind us, it emphasizes how precious and possibly unique we are. In that case, We could be one of the only sparks of intelligence in the galaxy, a rare chance for the universe to know itself. That realization carries a profound responsibility to survive and flourish. Because if we fail, there might be very little else in the cosmos that can carry on the light of consciousness. Of course, the great filter is not a proven law of nature, but a hypothesis born from our attempts to explain Fermi's paradox. Not everyone agrees on it. It might turn out that there is no single filter at all, just a combination of many unlikely steps. Or perhaps we simply haven't looked hard enough to find the others. Either way, the great filter is a thought-provoking way to frame the stakes. It reminds us that if we find simple life nearby and still see no advanced life anywhere, our future could be perilous. And if we find the cosmos barren of life, we might already be through the toughest hurdle. For now, it remains an open question, one that adds both urgency and wonder to our quest to understand our place in the universe. Now let's suppose for a moment that the filter, whatever it is, either didn't stop everyone or was never there at all. Imagine that at least a few civilizations in the galaxy have overcome all the hurdles. They survived, thrived, and continued to advance for millennia or even millions of years. What might such civilizations do? What wonders could they create? If they exist, we may detect them not by radio signals or messages, but by the colossal works of engineering they leave behind. This brings us to the fascinating idea of alien megastructures, enormous artificial constructions built by civilizations far more advanced than our own. An alien megastructure refers to any massive engineered construction on an astronomical scale. One of the most famous concepts is the Dyson sphere, proposed by physicist Freeman Dyson in the 1960s. It's not necessarily a solid shell, but rather a swarm of countless solar collectors or habitats orbiting a star, capturing most of that star's energy output. The idea is that a civilization far beyond our current level, often termed a Type II civilization on the Kardashev scale, would need energy on a scale vastly exceeding what a single planet can provide. By encircling their star with technology, they could harness power billions of times greater than what we use on Earth. To us, such a project is almost unimaginable, but to a society thousands or millions of years more advanced, it might be feasible. A Dyson sphere, or more accurately, a Dyson swarm of many structures, would allow a civilization to utilize a large fraction of their sun's luminosity for their needs. What would a Dyson sphere or similar megastructure look like to us from light years away? A fully enclosed star might not be visible in normal light at all, since the structure would capture the starlight. But that energy would be re-emitted as heat. Thus, a hallmark of a Dyson sphere could be an object that is dim in visible light, but very bright in infrared wavelengths, as if starlight were being absorbed and converted to waste heat. Alternatively, a partial Dyson swarm might cause irregular dips in the star's brightness as seen from Earth. Unlike the neat, periodic dimming caused by an orbiting planet, a megastructure could produce erratic or unusually deep dimming events. In short, the star might flicker or fade in a way that natural celestial objects usually don't. In 2015, a star known as KIC 8462852, better known now as Tabby's star, after the astronomer Tabitha Boyajian, made headlines for its bizarre behavior. The Kepler Space Telescope had observed this star undergoing strange, non-repeating brightness dips. At times it dimmed by 15%, even 20%, far more than a planet transit would cause. And the patterns didn't match anything like an eclipsing binary or a simple dust cloud. Natural explanations were hard to pin down. This mystery sparked speculation. Perhaps we were witnessing the signs of a partially built Dyson swarm, or some other alien megastructure passing in front of the star. Could an advanced civilization be constructing huge orbiting platforms, causing the star's light to drop unpredictably? It was a far-fetched idea, but for a while it captivated the imagination of scientists and the public alike. As more data came in, the alien megastructure hypothesis for Tabby's star became less likely. Follow-up observations and studies suggested more mundane causes. The star's brightness was seen to fade gradually over years, and different colors of light dimmed by different amounts during the big dips. Signs that something like dust could be blocking the light, since dust grains scatter and absorb light unevenly by wavelength. A solid megastructure would block all colors equally. The best explanation that emerged was a swarm of dusty fragments or cometary debris orbiting the star, creating an irregular cloud that occasionally obscures it. Over 200 astronomers contributed to research that concluded it's probably not aliens, but an interesting natural phenomenon. Though the mystery wasn't as exotic as a giant construction, it still taught us something new about the variety of things that can happen around stars. And importantly, it showed that looking for anomalies, however wild the initial explanation, is a valid part of scientific inquiry. Tabby's star reminded us that while we must be careful about crying aliens, keeping an eye out for the unexpected is how discoveries are made. Astronomers have conducted more systematic searches for potential megastructures. They've sifted through infrared sky surveys, like those from the IRS and WISE space telescopes, to find stars that are unusually bright in infrared compared to visible light. Such a signature could hint that something is capturing starlight and re-radiating it as heat. A handful of candidate stars with excess infrared have turned up, but none so far defy natural explanations. Most seem to be dusty star systems, or stars in a certain phase of evolution. Researchers have also looked for odd patterns in the light curves of thousands of stars, for anything that doesn't look like ordinary planets, hoping to catch a sign of something like a rotating structure or massive artificial eclipse. So far, nothing conclusive has emerged. This means no obvious Dyson sphere has been found yet. If they exist, they might be rare or not easily detectable with our current surveys. Megastructures need not be limited to Dyson spheres. Visionary thinkers have imagined other colossal feats. Ring worlds, for instance, a gigantic ring encircling a star at habitable distance, with the inner surface of the ring providing gravity and living area for trillions of beings. Or enormous cylindrical habitats, like O'Neill cylinders, spinning to simulate gravity, but scaled up to lengths of hundreds of kilometers. There are concepts of stellar engines, where a civilization could build a structure to move their star. One idea is a Shkadov thruster, essentially a vast mirror that uses light pressure to nudge a star in a desired direction. A sufficiently advanced society might engage in stellar engineering on unfathomable scales, like rearranging the architecture of their solar system or building planet-sized computers. One theoretical construct, the Matryoshka brain, envisions layers upon layers of computational shells around a star, using the star's energy to power a gigantic consciousness or simulation. These ideas verge on science fiction, but they remain within the realm of physics in principle, just extrapolated far beyond our capabilities. If any such wonders exist, they might reveal themselves through unusual observations, perhaps a star that drifts oddly due to being propelled, or a star that flickers as massive structures orbit, or maybe a peculiar spectrum of light that doesn't match any known natural source. Taking it to an extreme, consider a Kardashev Type 3 civilization, one capable of harnessing the energy of an entire galaxy. It's hard to imagine what that would mean in practice. They might dismantle star systems for raw materials, or orchestrate the energy output of billions of stars. Some scientists have humorously suggested that if we ever saw a galaxy that looked strangely faint or had an odd energy distribution, it could be a clue that someone has managed that galaxy. In fact, researchers have scanned surveys of galaxies to see if any have an inexplicably high infrared output, a possible sign of widespread energy capture. Thus far, none of the examined galaxies show clear evidence of this. They all appear to behave as natural galaxies do. If Type 3 civilizations exist, they are either extremely rare, not in our vicinity, or very good at blending in. As of now, no alien megastructure has been confirmed. But the very search for them expands our thinking. It forces us to imagine what a truly advanced technology might achieve. This search for technosignatures, signs of technology, complements the search for simple biosignatures like oxygen in an exoplanet's atmosphere. It means we aren't just listening for alien greetings, we're also mindfully watching for alien deeds. If one day we did detect a genuine megastructure, say a star with a peculiar dimming pattern and a big infrared glow that defies any natural explanation, it would arguably be one of the greatest discoveries in human history. Without needing to decode a message, we'd instantly know that intelligence can flourish far beyond our level. It would be a beacon of hope and wonder, telling us that in the dark expanse of space, great beings have risen and built and endured. Until that day, these ideas remain speculative, but they remind us that the absence of evidence is not evidence of absence. It could be just that we have more to learn and better methods to develop in our cosmic detective work. Pondering alien megastructures stretches our minds to grand scales. But there is one more leap that ventures even further. A leap not outward, but inward, into the nature of reality itself. We've considered that perhaps advanced beings could reshape solar systems or galaxies. Now we ask a deeper question. Could it be that our entire reality is itself an artificial creation? This is the realm of the simulation hypothesis. The proposal that what we perceive as the universe is actually a kind of simulation, a constructed illusion, perhaps run by an intelligence far beyond our own. It sounds like the plot of a science fiction story, but increasingly, it has been discussed by scientists and philosophers as a serious possibility. The simulation hypothesis posits that our reality, everything we see, experience, and are, might be a sophisticated computer simulation, something like a cosmic-scale virtual reality. Imagine an advanced civilization with technology so advanced it can model entire worlds, or even universes, with incredible detail. The idea is that such a civilization could create conscious beings within those simulations, beings like us, who do not realize that their world is not the base reality. In essence, we would be artificial intelligences living in a programmed environment, albeit one so rich and consistent that it appears completely real to us. While this concept is mind-bending, it's built on observations of our own technological progress. Every year, our simulations and virtual worlds improve. So we ask, might we ourselves be inside one, created by another mind? One influential argument on this topic comes from philosopher Nick Bostrom. He suggested that at least one of the following statements must be true. 1. No civilization ever reaches a level of technology capable of creating simulated realities with conscious inhabitants. Perhaps they destroy themselves first, or it's just too hard. 2. Civilizations that do reach that capability choose not to create simulations of the kind that would contain beings like us, maybe out of ethical concerns or lack of interest. 3. Advanced civilizations do run many simulations, and thus the number of simulated conscious beings far exceeds the number of real conscious beings. If that third scenario is true, then statistically, it would be vastly more likely that we are among the simulated minds rather than among the rare originals. In short, if it's possible to create simulated universes with beings who think they are real, and if someone out there is doing it, then the odds tilt towards us being inside a simulation right now. This kind of reasoning has led some prominent thinkers and even scientists to consider the simulation hypothesis plausible. A few have even put rough odds on it, speculating that it might be more likely than not that our reality is artificial. They often point to the trajectory of our own computing power. A century ago, the idea of a realistic digital world would be pure fantasy. Today, we have immersive video games and virtual reality experiences that, while still crude compared to life, have come astonishingly far. Extrapolate several centuries or millennia forward, assuming progress continues, and it's not hard to imagine being able to simulate not just a tiny slice of reality, but entire planets or minds with complete realism. If a civilization could harness something like a matryoshka brain, which we mentioned earlier, or quantum computing on a massive scale, the computational capacity would be enormous. They could potentially run simulations containing billions of beings with rich inner lives. And if they could, who's to say they wouldn't? Perhaps for research or entertainment or reasons we can't even guess. Thus, some argue, maybe it's already happened, and we are the simulated ones, not the simulators. Naturally, the next question is, if we were living in a simulation, is there any way we could tell? This is tricky, because by definition, the simulation could be designed to be indistinguishable from reality to those inside it. Still, people have speculated about possible clues. One idea is to look for glitches in the matrix, essentially errors or inconsistencies in the laws of physics. Perhaps at extremely fine scales, space and time might show signs of being digital, like the pixels of a screen. Scientists have actually considered whether the lattice structure used in some computational models of the universe would leave an imprint on things like the energy of cosmic rays. So far, no such anomalies have been detected. Physics, as we measure it, seems smooth and continuous. Another suggestion is that maybe we could catch the simulation updating or correcting something, though that verges on science fiction scenarios. If a phenomenon occurred that had no physical explanation, one might whimsically wonder if it was a patch applied by the universal software. But again, we have observed nothing that incontrovertibly fits that description. The simulation hypothesis also has a philosophical bent. It echoes age-old questions about reality and illusion. Long before computers, thinkers doubted the world as presented to our senses. Plato spoke of people seeing only shadows on a cave wall, mistaking them for reality. René Descartes mused that an evil demon could be tricking him with an illusory world. In Hindu philosophy, the concept of Maya describes the world as an illusion veiling true reality. The simulation idea is, in a sense, a modern, technological twist on these themes. It replaces the demon or the divine with a programmer or an advanced species behind the scenes. It's both a natural extension of our technology trends and a reimagining of ancient skepticism about appearances. If one day we found out that we are in a simulation, it would raise a multitude of questions. Who created it? Are they observing us now? What purpose does it serve? We might speculate that the creators are curious scientists studying universes. Maybe our whole history is a laboratory for them. Or artists creating for entertainment. Or even ancestors running historical reenactments of their own past. It's even been suggested that maybe the simulation isn't run by aliens at all, but by future humans trying to understand their origins. And then there's the emotional aspect. Would it make life feel pointless or insignificant to know it's not real in the fundamental sense? Perhaps not. If we are simulated, we still feel love, we strive, we create art, we experience joy and sorrow. Those experiences are real to us. Some argue that it shouldn't matter whether the quarks and electrons are real or just code, because the emergent reality we live is authentic to us. Others, though, might feel a sense of existential vertigo at the thought that everything is artificial. There are also strong counterpoints to the simulation idea. Many scientists are quick to note that it's currently not a testable hypothesis. There's no experiment you can perform that would definitively tell you this is a simulation. Without that, it remains in the realm of philosophical speculation. Some also argue that it might be exceedingly difficult to simulate a universe down to every particle. The resources required might be prohibitive, even for a super civilization, though clever simulation arguments propose only simulating what is observed, to economize on computing, etc. Another counter-argument is that perhaps consciousness, or quantum complexity, can't be replicated perfectly in a computer, implying there may always be a difference between a simulated world and a real one. In the end, the simulation hypothesis, whether true or false, is a testament to the boundless nature of our inquiry. It forces us to think outside the box, literally outside the universe as it were, and question the assumptions we take for granted. Even if we strongly suspect our world is real, entertaining the simulation idea can have a kind of philosophical benefit. It reminds us to be curious and not accept things at face value. It also places our own creations in a new light. As we build virtual realities and artificial intelligences, we are, in a tiny way, practicing the divine or cosmic craft that the simulation scenario posits at a grand scale. Real or not, the hypothesis doesn't change the tangible reality we must deal with. If you stub your toe, it hurts, simulation or no. We still have to live our lives, care for each other, and explore the world, or worlds, we find ourselves in. But it adds an extra layer of wonder, the idea that there could be more levels to existence than we realized. As science fiction as it sounds, it has people seriously contemplating questions like, what is reality made of? Can a simulation generate consciousness? Who, if anyone, sits outside watching us? These questions may never have definitive answers, but they encourage a mindset of humility. We might be very significant, as the only intelligent beings in a vast cosmos, or we might be one program running among countless others, our significance defined only by ourselves. Either way, the quest to know and understand is what drives us forward. In our journey through these deep space mysteries and theories, we've traversed an extraordinary range of ideas. We began by listening for alien signals in the quiet night, straining to hear a whisper from distant stars. We grappled with the Fermi paradox, the unsettling question of why, in a universe so vast, we seem so alone. We contemplated the great filter, wondering if there is a hidden hurdle that most life cannot overcome. We imagined the colossal works of alien megastructures, envisioning the fingerprints of beings far more advanced than us. And we dared to question reality itself with the simulation hypothesis, pondering if our universe is the ultimate cosmic experiment. Each topic carried us further toward the edge of knowledge, where confirmed facts blend into intriguing speculation. Standing at this edge, we feel both humbled and inspired. The universe is immense beyond comprehension, and many of its secrets remain veiled. Yet, the very act of seeking answers is a triumph of consciousness. Our ability to even conceive of these mysteries, to formulate equations about alien life, to dream up spheres around stars, to question our own reality, speaks to something wondrous about us. It is the mark of an inquisitive mind in a majestic cosmos. There is a deep calm in acknowledging that we don't have all the answers. It means there is so much more to learn, so much room for awe. Someday, perhaps, the silence will be broken. We might wake to the news of a faint signal finally picked up from a distant planet, or a strange light curve that can only be explained by alien architecture, or a microbe found on a moon of Jupiter, any of which would forever change our understanding of the universe. Perhaps we will find that we are not a solitary spark of life, but one among many points of light in a galactic sea. Or maybe we will discover that life is exceedingly rare, making our role as the universe's witness all the more precious. Either way, each possibility is profound, and each answer will raise new questions in turn. For now, on this quiet evening, we end our voyage of speculation and wonder. The radio telescopes still listen in the silence. The stars above still shine patiently, keeping their age-old secrets a while longer. We feel the depth of our solitude and, at the same time, the intimacy of being part of this vast cosmos. The universe has not given up all its answers, but it has given us the capacity to dream and to seek, and that is its own gift. As we conclude our exploration, we carry with us a calm reverence for the mystery of existence. The darkness of space is not empty. It's filled with our curiosity and imagination. As long as we continue to look up with wonder, to question bravely and listen carefully, we remain connected to the grand tapestry of reality, whatever it may ultimately be. In this spirit of humble inquiry and quiet hope, we close this chapter of our journey, grateful for the questions themselves and for the endless possibilities that lie just beyond the edge of knowledge.